Right, okay. All right, all right, all right. Right, okay. All right, all right, all right. Right, okay. All right, all right, all right. Give me maximum 1 minute. Give me some time. Okay. Right. This is the idea, right? Okay. Now the plan is now not it's not a big plan, but okay, already priority is completing the theory in our theory classes as I planned already. So then we start this class a few months before, but again we are starting for this 4 month. We are putting 100% effort and we are doing this class with our best. Okay, if I brief the idea, a small idea, right? Now this idea, right? We only have 4 months to be done. 4 months to go. No, 4 months to go. Okay. So then the plan is something simple plan. No? Okay. Listen. So right. Okay. Now what is the month? This month is April. April and May, June, July. Okay. So we have 4 months to go for the exam. We have 4 months for the exam, and I said there are three stories that we are doing from this month properly. One is our quick revision class, where we are discussing the theory points as soon as possible. We are not taking time and we are not going in deep, and we are not deriving anything, just roughly all the important theory points. In order to understand the possible questions and to do the full papers, I am giving kind of quick theory idea, a quick theory idea. So we only have 4 months, and I want to cover around 11 units in these 4 months. Okay. So under that revision program, another rapid revision program, listen very carefully, and not big story. The idea, the rough idea, rapid revision program. Okay, April month, I'm planning to complete once again Unit 4 entirely. Unit 4 entirely. Heat lesson entirely we are completing in April. Okay. April heat, and under the quick revision, rapid revision program. Okay, quickly revising all the important theory points in each and every section under heat. And I'm completing electric field also. I'm completing theory points. And let's say now if I have sufficient time, then I will start once again mechanics also. But we don't have enough time to complete all the mechanics theory points in April. But partially, if we have some time, section wise, I will do some mechanics unit 2 mechanics theory points also. Mechanics theory points also. And then March month we'll plan once again oscillation and waves. Somehow Unit 4 heat and Unit 6 electric field will be completely finished. A quick revision will be completely finished in April. May month let's plan Unit 3 oscillation and waves. Oscillation and waves will plan in May month. And May month we'll plan Unit 5 gravitational field also. Gravitational field GF in May, once again a quick revision. And also mechanics, again small sections, some sections in mechanics. Mechanics, some sections. And again, July, we'll talk about current, electricity, current, and in magnetic field, current, magnetic field, and in electronics ideas. Right, current, magnetic field, and electronics theory ideas. But if you have enough time, sometimes I will shift based on the available time. I will shift these lessons also. Sometimes I might start current quick revision in May, right? Current quick revision will start in May once again. Then electronics idea. And the last one is the last month we'll plan properties of materials and matter and radiation. Okay, this story. But remember now, the biggest problem is, right, okay, now our target is, remember, within these 4 months, our target is to do the past paper questions, enough number of past paper questions and revising theory points once again and parallelly doing set of full papers. That's our plan actually. But most of you, I think people who are going for the theory classes, for especially 2026 theory people, they don't want to worry that since they are still going for the theory classes, they can't remember these theory points. But the problem, especially if there are some students, they are going to do second or third shy. For them only the problem, because still sometimes some of you might expect a good result and some of you might not receive a good result. You didn't want to do the second show, third shy, but because of the result, you might do the second or third shy. So therefore, most of them doing second, third shy, the problem is they don't know the theories. They know the theories, but they want to kind of quick revision. So therefore, Tuesday morning we'll plan only. I'm not doing any question on Tuesday morning. Right, what's our plan is Tuesday morning we are taking the time and revising the theory points as soon as possible. Quickly we are revising all theory points. That's our plan on Tuesday morning. Why we are revising the theory points on Tuesday morning under revision class? Because my intention is to do the past paper questions from those sections. Okay, so Tuesday evening in our past paper class, past paper session class, what we are doing, right, what are the sections that we discuss under rapid revision class, in the evening, Tuesday evening, our paper class, past paper class, we are doing all the important past paper questions. I am prioritizing the past paper MCQ questions, but but what I am doing is once, when you consider 1 month, once in a month or twice in a month, I don't know, once in a month or twice in a month, we'll plan a kind of a full day. We'll take one full day and we'll discuss essay questions also. We'll put a one full day from morning to evening something once in a month, if not twice in a month. Based on your request, we'll do parallelly essay questions linked with those lessons also. Right, so then that is our main plan. So very simple. Tuesday morning we are doing a kind of quick revision, right? Entire unit 11 will be quickly revised in this Tuesday class, morning class, under rapid revision class. And then what we are doing is Tuesday evening, that is our main class, where we discuss past paper questions and we are practicing. But remember now, this week sometimes, since you won't get the tunes for upcoming 1 month, sorry, since you won't get the tunes for the next week, sometimes there may be some difficulties. But remember, there is a way of doing this past paper session hereafter. I told you. So daily, right, some managed for this upcoming 1 week. My plan is daily you are practicing 10 to 15 MCQs daily. Okay. Let's say we are planning to discuss our past paper discussion on Tuesday evening. So past paper discussion is on Tuesday evening. Past paper discussion is on Tuesday evening. Right, Tuesday evening, let's say 7 p.m. or 6 p.m. I don't know, 6 p.m. something. 7 p.m. 12 a.m. or 6 p.m. 12 a.m. I don't know, 6 p.m. onwards. Right? So then, so what you are doing is, for the last week, let's say now Tuesday means, let's say from Wednesday, Thursday, Friday, Saturday, Sunday, Monday. So daily you are practicing. I'm giving a book. I'm giving a tute. That tute includes section-wise, idea-wise, past paper MCQs. Right? If there are 6 days, then there will be 6 for a week. There are 6 past papers. There are 6 papers for a week, which includes 10 to 15 MCQs in each paper. So you are taking maximum half an hour. I will tell you those ideas, how long you want to take and how long you want to take and do the questions. Daily you are practicing daily 15 MCQ past papers, MCQ, MCQ, MCQ. Then our Tuesday class, what we are doing, I'm not sure that we have 45, 90 MCQs to be discussed on Tuesday class. That is not sure. But the most difficult sections, difficult questions, at least plan to discuss on Tuesday session around 50 MCQs maximum. If we do the discussion, pass the discussion class from 6 to 12 a.m., maximum I think we can discuss 50 MCQs, no maximum. We can give a small try for this. Then you can keep a time and you can try the past papers also. You might have tried the past papers before, but once again, daily 15 MCQ you can try by keeping a time and you can check your marks. Meantime, the discussion we are having on Tuesday evening. Then morning we are revising the theories. Then next Tuesday morning we are revising theories. For the next week, till the next week Tuesday revision class, you are practicing all the past papers. Then Tuesday evening we are doing the password discussion. That is our next story. And the next idea is we are doing that full paper practice also important. So therefore, meantime, this is the number one thing for if you're expecting to revise the theories, this is the best option. This is a best option. This option gives only the quick revision, kind of revision, but to get the ideas thoroughly, this is the next goal. Then if you want to practice the papers, let's say now Tuesday onwards, from this week onwards, not this week onwards, okay, next week onwards only I plan to give the paper. We are writing the paper. I thought of giving any time, right? You can Monday, Tuesday, Wednesday, Thursday. There are 4 days, but there is a slot. Morning slot is there. 5-hour paper writing. Okay, 5 hours, 2 hour MCQ and 3 hour essay. So then you can select any time slot and what you can do, you can write the paper. So then paper discussion is planning on Friday morning to 6 a.m. or 7 a.m. I don't know. From morning 7 a.m. to based on your request, okay. I will send the marking scheme also. Now for this upcoming 1 or 2 week, I will give the PDF version but give some time to post all the tudes. Thereafter, within 1 or 1.5 weeks later, you will get all the tudes. Then based on your request, I will discuss the full paper by taking the entire Friday. It depends on your call. No? Depends on your call. But anyway, 7 a.m. to 12 p.m. we are doing the discussion, full paper. And then again, we are starting from 2 to 6 p.m. discussion. Right, based on your request, let's discuss the entire full paper. That's better because there are still some points that we want to clarify in the paper discussions also. We'll do the full paper discussion. Means if the request comes from you in that way, means we can do that way. It's up to you. But that is the overall idea. Right? For only 4 months there, we'll work or put our maximum, we'll do it. That story. And this is the overall idea. And tudes, okay, tudes you will get within a week maximum you'll get the tudes. Don't worry, nothing to worry with that story. Right, okay. So now today my plan is unit 4 we are starting heat a quick revision from solid liquid gas expansions, and then we are starting unit 6 electric field intensity, electric force theory ideas. I am going to revise today. Let's say if I get enough time, I might start discussing mechanics 1 chapter row. Sometimes directly by taking the remaining time of today also, I start doing possible question discussion also. That is the plan. Now stay focused and learn. Right, okay. Idea. First idea. Okay. Idea. Okay. Right. So then we'll talk about today we are completing entire expansion stories. Entire expansion ideas. Right. So then so we know that under unit 4 heat lesson, heat. The first chapter is thermometry. I don't give priority for thermometry. First I am giving priority for the expansion. Expansion ideas. So expansion is basically, we all know that change in size or shape. That is what we call as expansion, right? I don't go deep and I don't explain. Expansion, we talk under three categories, three different categories. Expansion. The first category is, now whatever the important points, please write, prepare a kind of note by yourself. Prepare a kind of note by yourself, but I try to include all the important points I will write in the whiteboard. But you guys take enough time and write all the important points that I discuss today's class. Expansion idea. Expansion, we talk, we categorize to three categories: solid expansion, liquid expansion, and gas expansion. Solid, liquid, gas expansion, right? Solid expansion, solid expansion, then liquid expansion, and then the gas expansion. Gas expansion is discussed under gas laws. Today we are discussing all the theory points. Now, solid expansion also, we can talk about three types of expansions: linear, area, volume expansions. This today we know. Linear expansion. Then next one is area expansion. The last category is volume expansion. Volume expansion. So then the sub-story is linear expansion. The content is very high in linear expansion comparing with area and volume expansions. Normally we know that linear expansion is that is normally applicable for right, when we provide heat. We know what is the idea. When we provide heat, there are substances, solid or liquid or gas. They undergo kind of change in their size or shape, right? So if it is linear expansion, that is mostly applicable for a length, for a rod. When heat is provided, when the temperature of the rod is increasing, the length of the rod is increasing. When the temperature of the rod is decreasing, the length is decreasing. That is the idea, no? I don't go deep and I don't explain all the important points. Roughly I'm categorizing. Okay. Then linear expansion idea. Linear expansion. So linear expansion theory points. Okay. Theory points. Then let's consider now there is a rod. If we start from that story, there's a rod. Its initial length is its natural length. If not, we can tell initial length is simple L. This rod's initial length is simple L. Simple L. And this rod is at a temperature θ1. Rod is at a temperature θ1. And what you are doing, you are increasing the temperature by delta theta amount. If you increase your temperature by delta theta amount, what will happen? This rod will undergo expansion. Rod will undergo expansion means we all know length of the rod will be increased. Now, if you want to find the increase in length, so this is going to be the increase in length, right? There's a rod, its length is simple L initially. It is at θ1 temperature. And what happened is temperature increased by delta theta amount. Then if you want to find the increase in length, if that is what we call as change in length, this is going to be the change in length delta L. The first equation we learned is, remember, change in length is equal to what? If you can remember the equation we learned, first equation is this change in length delta L equals what? That is equal to L initial length alpha, that is somewhat a different story, delta theta. Change in length is equal to initial length into linear expansivity. Alpha is what? Linear expansivity. Delta L means we define it as delta L, we define it as what? Delta L, we define it as change in length, if not increase in length, when the length undergoes expansion, right? Change in length. Only important theory points I am doing. Change in length. Let's say now temperature of the rod is theta 2. Now temperature theta 2. Okay, no? Right, okay. So then, what is the relationship between theta 1, theta 2 and theta? So we all know that now temperature theta 2 is larger. Right? And now theta 2 is larger. Then if you want to find theta 2 is what? Theta 2 minus theta 1 is how much? That is delta theta. So simple, the first equation is under linear expansion. When there's a rod of length simple L, temperature increased by delta theta amount, if you want to find the change in length, delta L, that is equal to L alpha delta theta. First equation you must remember. Must remember. Okay. So then this idea, okay. Here alpha means linear expansivity. Alpha means linear expansivity. It's a constant which depends on the material. No? I told you linear expansivity mention a constant depends on the material. Linear expansivity. So remember, what is the units of linear expansivity? Linear expansion depends on the material. That story I don't give as a point, you write down. Next story is, remember, what is the units of linear expansivity? Remember, units of linear expansivity will be, okay, units of linear expansivity will be, right, it is measured in per Kelvin if not per Celsius. Per Kelvin per Celsius, this idea we know. Okay, no? Then the next idea is, next theory point is, first theory point is the first theory point. Theory point number 1, the second theory point is, okay, now if there is a rod, initial length is L1 when the temperature is theta 1 and temperature increased to theta 2 and now length of the rod is L2. What is the relationship between final length and initial length? That equation. Next story. Now, in that case, next theory idea, right? Next theory idea, right? Theory point 2. Theory point number 2. Theory point number 2, you must remember. Okay. Now same idea. Now initial length of the rod is simple L. Now length of the rod is simple L2. Temperature increased on the rod. Therefore rod undergone expansion. Right. Okay. Initial length is L1. And now length is L2. And I told you linear expansivity is a constant depends on the material. Linear expansivity of the material is alpha. Change in temperature is how much? Delta theta. Then we know that relationship between final length and initial length is going to be what? L2 equals final length is how much? That is equal to initial length L1. 1 plus linear expansivity alpha dot change in temperature delta theta. This equation, second theory point. We learn this idea also. In the theory classes I derive the stories, but now no need. This idea. And you have to understand delta theta means we all know that, right, now temperature theta 2, okay, large temperature, initial temperature is theta 1, that is smaller temperature, we know theta 2 minus theta 1 is delta theta, that idea is okay, no? Okay, second theory point, right, okay. So then this is for an expansion, then you want to understand when the temperature decreases for a contraction, what would be this equation? For a contraction, for example, when temperature decreases, the rod undergoes contraction, then the relationship between final length and initial length is what? L2 equals L1, 1 minus alpha delta theta equation. That story is clear. Next story. Next theory point. So then we talked about a point called fractional change in length. Next theory point. Next theory point is what? Fractional change in length. Okay. The next theory point is fractional change in length. Next theory point is, remember, fractional change in length. Okay. So for a contraction also I write down this story. When temperature decreases, remember, the length of the rod undergoes less than the length is decreasing. No? Therefore the final length is equal to L1 1 minus alpha delta theta. Please put an arrow and write down. This is for contraction. When temperature decreases, the relationship between final length and initial length is this equation. It's for a contraction, okay? For a contraction. Contraction. Now theory point number 3. Next story is we want to understand, we learned what does it mean by fractional change in length. Fractional change in length. Theory point number 3. I am telling all the important summary, okay? It's not the entire theory class, okay? Theory point number 3 is what is fractional change in length. Remember, fractional change in length means simply delta L, change in length over initial length. Okay? Fractional change in length. That is basically, remember, change in length over delta L over initial length is simple L. Right, to write down. Delta L is change in length over initial length simple L. If not, remember, you must remember there is another equation for the fractional change in length. One is delta L over L. Other equations, remember, alpha, linear expansion of the material into change in temperature. Alpha into change in temperature. That is a story. That story. Right, okay. So then remember, some stories, some ideas, some other small ideas linked with this expansion, linear expansion. Some ideas. Sometimes they can give a length undergoes expansion. They can ask you to do final length or something. But some scenarios they are telling examples like a circular coil. They can give a circular plate, rectangular coil. Some stories, small stories, okay? Small stories. Okay, these points you want to understand. Right? Small example ideas. Okay? Okay. Now example ideas, let's say now they can tell that rectangular plate, if not circular plate. Right? Rectangular plate, circular plate ideas. Look here. Now there can be a circular plate. And when temperature, initial temperature is theta 1, when the temperature increases to theta 2, right? When temperature increases to theta 2, what will happen? We all know this plate undergoes expansion. Right? So then at the diameter, let's say now initial diameter of this plate is circular plate is D1. And then the final diameter of the circular plate is D2. So we all know that when the plate undergone expansion, and now diameter D2 is greater than initial diameter D1. Remember, same idea, temperature increase by delta theta, linear expansivity is alpha. Remember, if you want to find now diameter D2, that is equal to D1 1 plus alpha delta theta, same idea. Right? For a rectangular plate also, same idea. For a rectangular plate, let's say now at theta 1 temperature in the beginning, temperature increase by the theta amount, rectangular plate undergoes expansion, this plate. Let's say initially the simple A, length is simple A, rectangular plates, and with a simple B. Now length of the rectangular plate is simple A dash something. Now width of the plate is simple B something. If you want to find the final length, again you can do same equation. A dash equals A 1 plus alpha delta, same equation, same idea, same story. Circular plate diameter, and also if you want to find the perimeter, let's say now in a circular plate the perimeter is C1. The perimeter of the circular plate is C1 at theta 1 temperature. After the plate undergone expansion, if you want to find now perimeter C2, again C2 equals C1 1 plus alpha delta theta. If the radius of the circular plate is R1 and now radius is R2, then also you can write down R2 equals R1 1 plus alpha delta theta. Same story, same idea. In the theory classes I took time and explained this idea. And also remember, for a gaps also we can apply this equation. This equation we can apply for a hollow gap. Next story. Next story. For a hole or gap also we can have this equation for a hole. For a hole, let's say now there is a plate. There's a plate. Okay. Now only important points I'm categorizing. I don't deriving anything because theory we want to complete. We can finish it. Then for a hole, okay, there's a plate. In the plate there's a circular hole. Thing like that. At theta temperature. And let's say the diameter of the circular hole is, remember, that is d1. Now some people think like when the this plate having a hole undergoes expansion, diameter d1, the plate undergoes expansion. Remember, not only the plate but also the hole also undergoes expansion. Not only the plate undergoes expansion but also the hole also undergoes expansion. So therefore now plate is also undergoing expansion. Also hole also undergoing expansion now. Do you understand? So now diameter of the hole is simple d2. Now diameter of the hole is simple d2. Today we are doing these past paper questions in today evening class. I give you the idea roughly, and today evening when I do the questions you will understand more. That's the way. Revising theories, and we can't do some example questions in this session. This day is only for revising the theory point only, but in the past paper class what we are doing, we are doing all the past papers linked with these ideas. Okay, no? Then if you want to find the before hole diameter is d1, and now hole size also increase. Now diameter of the hole is d2. If you want to find the d2 equals d1, 1 plus alpha delta theta equation. This story. These are the ideas, right? Are very simple ideas. Then this is the overall content of linear expansion. If you can remember these theory points, delta L theory point 1, theory point 2 and theory point 3, and these concepts. Okay, gaps also. Whenever there's a gap, look here, whenever there's a gap, whenever there's a small gap, then enough. Then we can talk about area expansion. So whenever there's a gap, let's say now there's a circular wire. The circular wire has a small gap. Let's say this length of this gap is L1, right? At theta 1 temperature. The temperature increase, remember, not only the circular wire undergoes expansion, but also the gap also undergoes expansion. And now gap is increased. Now the circular wire also expanded, the gap also increased. Okay. Now the gap also increased. If you want to find the now length of the gap, that is simple L2. Again same idea. Now temperature theta 2, temperature increased by delta theta amount. Therefore now gap L2 is how much? L2 equals L1 1 plus delta theta. This is the overall content regarding the linear expansion idea. This is the overall idea. Now we'll talk about area expansion, volume expansion. Okay. So then what shall I do? I want to teach you some points regarding there are some applications. Remember linear expansion, there are some troublemaking two applications are there. One is simple pendulum time period deviation with the change in temperature story, and for a linear scale, how this expansion impacts when taking measurements from a linear scale. Those are two troublemaking examples in linear expansion. But overall content is clear. Today when you do the past paper story, every point you will understand more clearly. That idea is okay. Next to this area expansion, same idea. Area expansion. Now still I'm talking about solid expansion. And area expansion theory points. Important theory points, area expansion. Next idea, area expansion. Right, all the important points you quickly mark down. Area expansion, right? We should give more time to do the past papers and get the ideas. That is the right way. Theory points, revising only the theory points soon, and target is do more past paper questions. That's our target. Parallelly practicing some full papers. That's our target. That is the right way of practicing exams. That's the right way. air expansion. No, same idea. Now, like how when temperature changes, like how length of a rod changes its length, similar manner when you consider a area, mostly this story is applicable for a very thin plate. It can be a metal plate, very thin plate. When temperature increases, what will happen for that very thin plate? It undergoes expansion. I don't go deep and I can't explain like theory class. Only the brief points, only the summary points I'm explaining. Only the brief idea explaining, only the brief idea. Only the very brief idea I'm explaining this story. Okay? Only the summary, oral idea. Right, okay? Now again, now area expansion also. Now first theory point number 1. Area expansion, theory point number 1. You want to understand, you should remember the equation for change in area in a plate. Theory point 1. Right, theory point area expansion. First theory point is let's say now there's a metal plate at theta1 temperature. The area of the metal plate is capital A1. The area of the metal plate is capital A1. That's a metal plate. Okay. The temperature is capital theta1. Let's say area of the metal plate is capital A. Capital A. Area. The surface area is capital A. When the temperature increased by delta theta amount, we know that this metal plate undergoes expansion. Therefore, the area of the metal plate increases. Let's say the increase in area is delta A. Temperature increased by delta theta amount. Now the metal plate undergone expansion. Now the metal plate undergone expansion. Now the metal plate undergone expansion. Right? So then now temperature of the metal plate is theta 2. So we know now temperature increased, no? Therefore theta 2 minus theta 1 is delta theta. No? Change in temperature is equal to how much? Large temperature minus smaller temperature. That is okay, no? That is okay, right? That small part, no? Then if I mark this initial area in the plate, this was the initial area of the plate, capital A1. Capital A1. This was the initial area of the plate, capital A, okay, capital A. Then what is this area? This area is going to be the increase in area, if not change in area. Change in area. This area is delta capital E. Delta capital E. Delta capital E. Then we learned an equation to find the change in area. It can be, if it undergoes thermal expansion, it is going to be increase in area. If it undergoes thermal contraction, it's going to be decrease in area. So delta A equals what? Delta change in area equals what? Initial area is capital A. Now capital beta. That is what we call as the area expansivity. If not, we can write down coefficient of area expansion. Write down this simple alpha means linear expansivity. If not, coefficient of linear expansion. A capital beta delta theta. This equation story. This equation idea. Clear, no? This idea is clear, right? Remember here, capital beta is a constant which depends on the material. This beta is what we call as what? Beta is what we call as area expansivity. Area expansivity. Area expansivity. Remember, this constant also depends on the material. Remember, there is a relationship between area expansivity and linear expansivity. That is what, remember, area expansivity is always twice the linear expansivity of the material. In the exams, they don't give beta. Normally, they give the alpha. But from this alpha, you want to write down an expression for the beta. Beta equals 2 alpha. No? This story also important, very important point. Right. What can we say about the units of air expansion? Remember, same as per Kelvin per Celsius. Units of air expansivity. Units of air expansivity beta is, remember, beta units, remember, per Kelvin or per Celsius. I don't show how beta is going to be, why you are telling beta unit is per Kelvin or per Celsius. The derivation part, everything I can't explain here. I'm only focusing theory points. Right, okay, no? The story is also okay. Then second theory point is, let's say now if we have initial area, if there's a plate having initial area capital A1, it undergoes thermal expansion. Now the final area is capital A2. What is the relationship, equation, which links final area and initial area equation? Same way, same idea. Same idea, same idea. Theory point number 2. Theory point number 2, second theory point. Theory point number 2. Second theory point. Let's say now there is an area that is capital A1. This area is capital A1. And the initial temperature is theta 1. Temperature increased by delta theta amount. And now the area is capital A2. Now the area of the plate is capital A2. Capital A2. Capital A2. Now the area is how much? Capital A2. It's capital A2. Now temperature of the plate is capital theta 2, right? What is the equation which provides the relationship between final area A2 and initial area capital A1? We learned that capital A2. We know that capital A2 final area equals initial area 1 plus beta. If not, one can substitute 2 alpha as well. 1 plus beta delta theta equation. Story. You must remember these equations. Without knowing these equations, you can't do past paper questions. You can't do questions. And I don't draw the next scenario. When temperature increases, area this plate undergoes expansion. What about when temperature decreases? Plate undergoes contraction. In that case, area decreases. In that case, final area equals what? Initial area. Final area equals initial area 1 minus beta. 1 minus beta delta theta equation. Right now, area expansion idea, right? Normally I take, generally I took I think around 1 month to explain expansion theories in the theory class. But revision classes, we don't take that much of time, only important equations and important core ideas. Because if we start explaining about theory point, it's going to be theory class. Right, okay. Other theory point number 3 is, next one is, they can ask you, they have asked in the exams also, next theory point is fractional change in area. Theory point number 3 is fractional change in area. Fractional change in area, next theory point. You get the 100% benefit of this revision class if you join for the paper class only, passable class. Then only with what we learned today morning, today night, we are doing the questions. Then session is going to be very effective. Where if you are planning is revising within 4 months, everything once again means that if that is your motive, within these 4 months to revise the story, this is the only option. Right? If not, we can't revise everything, no? 4 months entire syllabus. Practicals, don't worry, I have an option. For the people, if you want to get the practical revision, we are doing practicals separately, don't worry. Practicals we are doing separately, don't worry. Right? Practicals we are doing separately, don't worry. Practicals we are doing separately, don't worry. Okay? Don't worry. Okay, don't worry. Practicals we are doing separately, don't worry. Quickly write these stories. The stories write down so quickly. Write the stories quickly. Quickly write down. Quickly write down. Other theory point number 3. Third theory point, write down the third theory point. Theory point number 3 is what? Theory point number 3. Theory point number 3. Number 3. Okay. Fractional change in area. Fractional change in area. Change in area. That is equal to what? Remember, change in area over initial area. Remember, fractional change in area means, remember, that is delta A over capital A. Delta A over capital A, that is first equation for fractional change in area. If not remember, that is equal to beta delta theta. Remember, fractional change in area means, remember, beta delta theta. If not remember, beta is what? Beta is 2 alpha, no? 2 alpha delta theta. Remember, fractional change in area is, remember, that is beta delta theta, beta into delta theta If not 2 alpha into delta theta. Do you understand? Right, beta into delta theta. If not 2 alpha into delta theta. Right? If not 2 alpha into delta theta. This idea. Then this is the overall theory about area expansion. Right? Normally we don't talk beyond this idea. This theory content is more than enough for area expansion. Last idea is volume expansion. Then overall theory point wise solid expansion is the overall content. But I will tell you some applications in linear expansion story after explaining some ideas, right? Then volume expansion theory points. Volume expansion, or if you can remember these points more than enough, you can try almost all the questions in papers. You can try almost all the questions in the papers if you can remember these points. If you can remember. Right. Next one is volume expansion. Next one is volume expansion. Volume expansion. Volume expansion. Volume expansion. Volume expansion. Right? Now here, volume expansion, again same three points. But same idea. Same idea repeating again and again. Same idea repeating again and again. No any difference. Then let's consider the first theory point is if you want to find the change in volume, there is a volume which is suitable for any object having a volume. It can be applied for a solid cube, right? Solid cuboid, whatever, right? It can be for a hollow cuboid, whatever. Initial volume of the hollow cube is, let's say, V, and when the temperature of that solid or hollow cubes increase by delta theta amount, if you want to find the increase in volume, delta V. If you want to find the increase in volume, delta V, that equation, delta V equation, right? Theory point number 1, first theory point, right? Theory points. From beta we put point number 1, 2, 3, point number 4, 5, 6, no? Point number 4, 1, 2, 3, then point number 4, 5, 6, no? Point number 4, and point number 5, and point number 6, then point number 7. Theory point number 7, simple idea, right? Now initial volume of that object is capital V. Initial volume is capital V. Volume is capital V. Capital V. And the temperature increase by delta theta amount. The now volume is capital delta V. Now increase in volume. And now the change in volume is, remember, that is capital delta V. Now change in volume is remember, that is delta V. The change in volume going to be delta V. The change in volume is, that is delta V. Okay, no? Right, okay. Initial volume is capital V. Volume expand, okay, initial volume is capital V. Temperature increase by delta theta amount. Then the now change in volume, now increase in volume of this object is delta V. Change in volume, okay? Increase in volume. Change in volume is delta V. Then if you want to find the change in volume, whether it can be increase in volume for expansion, if not, it can be a decrease in volume during a contraction, delta V. Anyhow, delta V equation is, remember, that is initial volume into gamma, volume expansivity, into delta theta, change in temperature. This idea we know. Remember here, gamma means volume expansivity. And that is also a constant, depends on the material. Its unit is per Celsius or per Kelvin. But remember, volume expansivity, if not, we can call it as coefficient of volume expansion. Volume expansivity, if not, we can call it as coefficient of volume expansion. Volume expansivity, if not, we are calling it as coefficient of volume expansion. Its unit is going to be per Celsius or per Kelvin. Same, per Celsius or per Kelvin. Remember, volume expansivity, gamma equals 3 times alpha, thrice the alpha. 3 alpha is the gamma volume expansivity. Remember, we can write on volume expansivity in terms of the area expansivity, 3 over 2 beta. 3 over 2 beta. You understand? Gamma equals 3 alpha. Volume expansivity in terms of linear expansivity, gamma equals 3 alpha. If not, gamma equals 3 over 2 beta. You must remember this idea. Must remember this idea. You must know. And also the next theory point is, let's say next theory point is the next theory point, let's say now point number 8, let's say now there is a object initial volume at theta1 temperature is V1 and temperature increased by little theta amount, and now final volume of that object is V2. If you want to link final volume and initial volume, now story. Now story is, remember, I don't know the diagram. I hope you can know the diagram. No, initial volume is V1, final volume is V2. Then theory point number 8, remember. Theory point number 8, remember. Theory point number 8, remember. The next story, next idea, we can write down final volume V2 must be equal to initial volume is V1 inside the bracket 1 plus gamma delta theta. Okay, 1 plus gamma delta theta. If not, if it is a contraction, let's say there is a volume V1 initially, when the temperature decreases, that volume reduces, undergoes contraction. In that case, if you want to find final volume, that is what? Final volume V2 equals what? 1 V1, 1 minus gamma delta theta. This idea. I didn't draw the diagram, but you can draw the diagram. No? Just draw a diagram, 2 boxes. Initial volume is V1, final volume is V2. This story. Remember from this summary, okay? This story, highlight. This story, highlight. This story, highlight. The last theory point is, remember, the fractional change in volume. Fractional change in volume, the last story. Then overall solid expansion content is finished. The last story is fractional change in volume. The last story. Theory point number 9. Theory point number 9. Theory point number 9. Fractional change in volume. Right, fractional change in volume, the last theory point. Fractional change in volume. Change in volume. Remember, this is also what? Change in volume. Fractional change in volume is equal, remember, delta V over change in volume over initial volume. That is equal, remember, gamma delta theta. Fractional change in area is b delta theta. Fractional change in length is alpha delta theta. Likewise, fractional change in volume is, remember, gamma into delta theta. So we can write down gamma means 3 alpha into delta theta. Gamma means we can write down 3 beta over 2 into delta theta. You can modify accordingly. So this is the overall summary that you want to put in your mind. If you have the summary in your mind, definitely you will understand today. Today we are doing all the past papers. I'm trying my maximum to do. Today we'll start from 6 p.m. Today we'll start from 6 p.m. and evening will with these theory points. I'm pretty much sure that, right, this is a kind of revision, right? We can't, within 4 months, we are quickly revising all the theory points. Now we are revised the theory point is the content. This content is more than enough. Right, from this content, you will understand today all the past paper questions came in from 1992 2025. We are doing set of questions, right? Then you can understand the story nicely. It's the oral content of solid liquid solid expansion idea, right? Now clearly simple story. Now all good. If this idea is very clear, just put a small. If you have that YouTube account, put a small thumb in the YouTube chat. Normally we do the class in Zoom. Only today only we are doing just since it's our first class. I am streaming, right? Then today evening class also streaming via the YouTube. Then next week onwards we are going the usual Zoom story. Put a small reply in the Zoom. All clear. If every point is very clear, put a small thumb. Put a small thumb in the YouTube, and I'll give some time for you to write these stories also. I'll give some time. Give a small try. Time is 8:38. I will give around 5 minutes to write these stories nicely. And if all clear, put me small reply. Just put a small reply. If all okay, just put a small reply also. All okay, no? All okay, simple story. This story is very simple story, right? Very simple story. Now the most effective class is not this is effective only. The very effective class is today's past paper class. Hereafter consecutively, whenever we have time, every day we put the time and we'll do the story properly. We'll practice more questions. That story, that story, that story. Okay, no, right? No, simple, no. Simple story. Time is 8:39. We are starting then liquid expansion theory ideas at 8:45. Then gas expansion. Then we are going back to the electric field theory point. And if I have time, I will start that some mechanics, fluid dynamics theory points. Now I will start revising mechanics once again. Fluid dynamics theory points also I am revising. Okay, in that way. In that way, theory points. Let's give a small try. Let's give a small try. Right, okay. So then this chapter, this section done, solid expansion, theory, idea, this content, okay. From this content, trust me, today all the past papers, including MCQ, structured essay, you can try any question from any A-level exam. Okay, this content here, clear ni? Linear expansion, then solid expansion, entire theory idea clear, theory points are clear, very clear, no? Very clear. And then we'll talk about liquid expansion idea, liquid expansion core ideas, the core theory ideas. The core theory ideas in the liquid expansion. Core theory ideas in liquid expansion. The core theory ideas. Right. Right, okay. The first theory point you want to know regarding liquid expansion. Now story is liquid expansion. This is somewhat complex than the solid expansion, but idea wise okay. Liquid expansion theory points. Liquid expansion, right? Remember some points regarding liquid expansion you want to know. Remember when you compare a solid and liquid, remember what is the main difference? What is the main difference between solid and liquid? We all know that solid has a fixed volume as well as solid has a fixed shape. But the thing is, liquid does not have any fixed shape. Always liquid obtains the shape of the container, right? If you put a liquid into a rectangular container, the shape of the liquid is rectangular shape. If you put the liquid into a kind of cylindrical container, the shape of the liquid is going to be a cylindrical shape. Therefore, remember first important point is remember. The first point is remember liquid has a fixed volume, but they don't have a fixed shape. Liquids, they don't have fixed shape. Right? The some theory points. Okay, theory point first stories. Remember these liquids, they don't have a fixed shape, but they have a fixed volume. Right? Liquids, they have a fixed volume. They have fixed volume, but they don't have a fixed shape. They don't have a fixed shape. Okay, right? They don't have a fixed shape. This story is okay. Right, okay. Now, the next important thing, remember, you want to understand is just consider a solid and generally when you consider a solid and liquid, right, of equal volume, there is a solid and a liquid of equal volume. For example, solid means just consider a metal block of volume capital V, and for a liquid consider water volume of capital V, right? Solid and liquid have same volume. Let's say if you increase their temperature by same amount. First theory point, remember, first theory point is the core idea. Theory point number one regarding liquid expansion. Now there is a solid and liquid. There is a solid and liquid. Right, initial volume of the solid is also capital V. Liquid volume also capital V. Liquid volume also capital V. Liquid volume also capital V. All right. Okay. Now, if you increase the temperature by same amount, solid volume also initial volume is capital V. Liquid also having initial volume capital V. When temperature is increased by same amount delta theta. When temperature increased by same amount delta theta, remember, generally, expansion of the liquid is always greater than expansion of a solid. Generally, remember, expansion of a liquid is always greater than the expansion of a solid. Okay, let's say now, for example, now solid expanded solid also undergo expansion. Liquid also undergoes expansion. Liquid also undergoes expansion. But remember, if I say expansion of the solid is delta V1, if delta Vs, expansion of the solid is delta Vs. Not the final volume of the solid, okay? This is delta Vs means what? Increase in volume of the solid. If not expansion of the solid, that is delta Vs. And also if I do the expansion of the liquid, that is delta VL, L for liquid. Remember, generally, when you consider equal volume of solid and a liquid, and if you increase their temperature by same amount, generally remember, expansion of the liquid is greater than expansion of the solid. This story is the key point, the key theory point. Key theory point. Then okay, next theory point. Next theory point. This idea is clear. Next theory point. The next theory point. Next theory point. I mean, theory classes I go deep and explain, but here it's a revision, only important points. Next theory point. Next theory point. Right? To get this idea, I told you liquid have a fixed volume, but it does not have a fixed shape. To explain this idea, you can take different shapes of container, no? Different shapes of container. When you fill, if you insert 1 liter water to a rectangular shape, that liquid also going to obtain a kind of rectangular shape, 1 liter. Right? Similar manner, if you take a kind of spherical shape container, if you insert same 1 liter volume, it's going to obtain the same volume but different shape, spherical shape. That is the idea. That core idea is you understand. Therefore, it does not have a fixed shape, right? And point number 1 is very important point, very core point. This is the core point. Next theory point number 2. Theory point number 2, right? So theory point number 2, next story. The second theory point is, remember, right? Second theory point, very important point. The very, very important point. Okay. Second theory point. Theory point number 2. Theory point number 2. Now we talk about this story. We insert a liquid in a container, right? There's a container that is at a certain temperature, and we are inserting a liquid in a container. Then we are telling that liquid is completely filled in the container, right? That story. There is a container that is a solid, and a liquid is filled in the container that is a liquid. Both are at same temperature. Thing like that. Thing like that. Right, thing like that. We are starting Unit 3 practicals very soon. This week or next week, first Monday mostly. Right? Okay, this idea. I don't go in deep explanations, but all the important theory points I'm explaining. Anyone at any level can understand these stories. Don't worry. Don't worry. Right? Now, this is a container that is made with a solid, no? And then a water, or not water, a liquid is inserted into the container. That liquid is completely filled in the container. Think like water is filled completely. Okay, no? Right, that is okay. That is okay, right? A liquid is completely filled in the container. If I ask you what is the initial volume of the water, and what can you say about the initial volume of the water, and what can you say about the volume of the container? We all know that volume of the container and volume of the liquid is same. Liquid volume and container volume both are same. Let's say initial volume of the liquid is also capital V if it is completely filled in the container. And also initial volume of the container also capital V. It's a capital V. Initial temperature is, let's say that is initial temperature is that is theta 1. Theta 1. Remember the temperature of the liquid as well as temperature of the container both are theta 1, okay? Some theory points. Now remember, that means now liquid and container both have same initial volume. What if I increase the temperature by theta amount? If I increase their temperature by theta amount, understand liquid and container both undergoes expansion. Both of them have same initial volume. Solid and liquid, container and liquid have same initial volume. Temperature increased by same amount. Then I told you, since liquid expands more than solid, what will happen is some amount of liquid will overflow. Since liquid expands more than solid, some amount of liquid will overflow. This idea we learned. Overflow. Then we'll talk about gas laws, all theory points. Then we'll start about electric field, that theory point idea. Then fluid dynamics theory point idea also will start. But the more time we require is past papers. We require a huge time. We require a very huge time. This is the core idea. If you understand this core idea, then liquid expansion idea is finished. This is the number one idea, right? Then the solid container also expanded, and the liquid also expanded. Some amount of liquid is overflown also. This is that overflow liquid volume for our understanding. Right? Okay. The thing is, if I mark this initial volume of the container in this scenario, in this diagram, if I mark this initial volume of the container in the final volume of the container, right? This idea, 9 o'clock, no? This idea, right? This idea. So we all agree. What is the increase in volume of the container? We all agree, sir, increase in volume of the container is this much. No? Initial volume of the container is, this is the initial volume of the container. Then what is this volume? This volume is going to be the increase in volume of the container. Increase in volume, no doubt. No doubt, okay. I'm telling summer revise only, I'm teaching. When I do explanation, normally I take time and explain. But here we can't do that story. We can't do that story. This is going to be the increase in volume of the container. It's blue color. This one is going to be the increase in volume of the container. Right now. That is, let's mark it as right. So therefore, this is the increase in volume, if not volume expansion of the container. No? But therefore, you can tell this part is going to be what? Volume expansion of the container. Right? Volume expansion of container. Volume expansion of container. Volume expansion of container. That is this volume, no? This volume. For our understanding, I just do that part. For our understanding. But when I do the past paper questions, I will give different theory point ideas. I will ask you to write down those ideas in your separate short note point book. Okay, no? Right. It's okay, right? I can't take that much of time. I want to finish this idea and I want to go to next story. Right, okay. And if I ask you what is the total expansion of the liquid, the total increase in volume of the liquid. Now, if this is the initial volume of the container, this is the initial volume of the liquid, no? And now, if you want to find the increase in volume of the liquid, this is this volume plus overflow liquid volume, no? But this is also filled with liquid, no? This volume plus overflow liquid volume going to be the volume expansion of the liquid, if not increase in volume of the liquid. Overflown liquid volume. Right? Second theory point is very important theory point. This is very important theory point. So if I write down volume expansion of the liquid, if I draw the volume expansion of the liquid, second theory point, right, volume expansion of liquid. So then that is going to be what? That is going to be this part plus this part. Again I have to draw, no? This is the number two core theory point. Okay, this is the core theory point. Nothing else this much complex in these theory points. Second important theory point is this one. Understanding what is the expansion of the solid and what is the expansion of the liquid is the number 2 important point. Right now, this story is okay. 9 o'clock, we start the class exactly at 7:45. Time is 9 o'clock. We covered solid expansion theories. Now we are covering liquid expansion. Somehow we can complete the plan, the story. Day by day, we are effectively in the class. But I am really focusing more past papers. That's my target. By doing past paper questions, I won't teach you the 80 points. That's my target. Then we complete the past paper stories also. Then we are raising theories once again also. That's my target. This revision class is really suitable if someone is want to revise the theory points once again. If you are doing the first shy in 2026 A level, then for you, obviously that's a kind of support from these sessions. But especially the people who are doing second, third shy, because they can't remember some theory points at least. For them, this is very effective. For 26 first shy people also effective, but mainly second, third shy people, this is very, very effective. Okay, this way today evening class you will understand. And then plus overflow liquid volume idea clear. This story clear, no? This idea clear, right? Okay. Second theory point clear, no? Second theory point, right? Okay. Now we talk about in liquid expansion, solid expansion also. We talked about linear expansion, area expansion, volume expansion. In solid expansion, then we talked about linear expansivity, area expansivity, volume expansivity. In liquid expansion also, we are talking about two types of expansion: the real expansion and real expansion, if not absolute expansion, and apparent, if relative expansion. So this is the bit confusing section, the real expansion and apparent expansion. That is what confusing story, right? Therefore, I want to take some time to explain that idea. Only that idea will take some time. Just imagine this scenario. If you have a kind of kettle, just consider a kettle or kind of container that you fill water completely, and you are going to boil the water in the intention of preparing a tea, right? Definitely we know that when the temperature increases, when you heat the water with the container, we all know that temperature of the water as well as container increases. Definitely container also undergoes expansion. Water also undergoes expansion, and according to this theory logic, some amount of water will overflow. No? If you fill water completely in the container, when temperature increases, container as well as water both undergo expansion. Since expansion of water is greater than the expansion of the container, some amount of water will overflow. But do we see, are we able to see, we can see that water is overflowing from the container, we can see water is overflowing from the container, especially if you fill the completely milk completely into the container, and we have seen that the milk is overflowing. We can clearly see that water is overflowing from the container. But can we see from our naked eye expansion of the container? Even though I show that container has expanded this much, but in practically expansion of the container is very small. We can't see clearly. Yes, there is an expansion of the container. There is an expansion of the solid, but the problem is we can't see the expansion very much clearly. Therefore, some people think like actually container also expanding, but we can't see container's expansion. Therefore, some people believe like expansion of the water, expansion of the liquid is only that overflow liquid volume. Right? Some people they believe, but actually we know there is an expansion in the container. The problem is we can't see the expansion of the container clearly for our naked eye. When the container expands, we know some amount of increased volume storing in this location also. But we can't see that story, no. Therefore, most of the people they believe like expansion of the liquid is only the overflown liquid volume, overflown water volume. Then For our eye, for our naked eye, we can see only the off-flown liquid volume as the expansion of the water. No? We can, for our naked eye, what we can see is off-flown liquid volume. That is what most of us consider as the expansion of the liquid. But we know, so actually expansion of the liquid is not only the off-flown liquid volume, but also this volume also we want to add. Then only we can get the exact, actual, real expansion of the liquid. No? We want to add off-flow liquid volume plus this volume of the liquid. If we add only, we can obtain a real expansion. If someone considered only that off-flow liquid volume, that is only the apparent, for our eye, apparent expansion. Then very clear, what is real expansion? That idea, real expansion of a liquid means, if you take entire really, what is the total increase in volume of the liquid? That is we call as real expansion. This is what we call as real expansion. Real expansion. Okay. Summary I am teaching. Okay. Real expansion theories I take so much of time to explain. Real expansion. If you only consider the overflow liquid volume, that is the apparent expansion. Real expansion means these two together. If not, okay, if you take these two together, that is real expansion. If you only consider overflow liquid volume, that is what we call as apparent expansion. That is what we call as apparent expansion. That is what we call as apparent expansion. Right? Just mark the stories. Right. So then if you only consider the overflow liquid volume, that is going to be the apparent expansion. Apparent expansion. Apparent expansion is very important core theory idea. Core theory. If you know this idea, you can do any liquid expansion question. Apparent expansion. Apparent expansion. Right, this idea. This idea. Then very clear, no? Then if I want to find the volume expansion of the container, this is the volume expansion of the container. Right? If I want to find the volume expansion of the liquid, the real volume expansion of the liquid is this volume plus this volume. If I want to only find the apparent expansion, only this volume. This story. This story. This story. This story idea. Let's quickly write these stories. This stories quickly write down. This stories quickly write down. These stories write down quickly, very quickly. What are the stories? Write down quickly, very simple story. Next theory point number 3. Theory point number 3. So if I want to find the actual expansion of the liquid, we can use, okay, same story. If you want to find the actual expansion of the liquid, look here, the actual expansion of the liquid we can use, right? Look here, very simple, okay. Okay, if I want to find the theory point number 3, third theory point. Okay, theory point number 3, next theory point, remember. Theory point number 3. Theory point number 3 story. Okay. Then, if I want to find the real expansion of a liquid, actual expansion. If I want to find the real expansion. If I want to find the real expansion. The real expansion. Real expansion. That means actually what is the increase in volume of the liquid? Actually, how much volume is increased in the liquid? Real expansion. Real expansion. There is delta V. That is delta V. Real expansion is, let's say, that is delta V. Real expansion delta V. Delta V. The equation to find the real expansion is, remember, these two, this delta V, the addition of these two volume going to delta V. The equation is, remember, delta V is initial volume of the liquid is V. Gamma means, remember, real expansivity. Now, same story. Remember, gamma means what? Real expansivity. Delta theta is what? Change in temperature. Got it? What is gamma? Gamma means, remember, gamma is, remember, that is real expansivity. Gamma means, remember, that is real expansivity. Gamma is real expansivity. Real expansivity. The units of real expansivity also same as per Celsius per Kelvin. Real expansivity. Real expansivity. The units are, remember, gamma units are, remember, per Celsius or per Kelvin, same story. And if you want to find the relationship between, now initial liquid volume is V1, if you consider, okay, the next story is, okay, initial liquid volume is V1, and if you want to find the final liquid volume V2, that equation, remember, that equation, right? And now theory point number 4. That's it. Theory point number 4, remember. Theory point number 4. Okay. In this scenario, if you want to find the, let's say now there is a container, there is a liquid. Just consider only the liquid. In a container, there is a liquid. In a container, there is a liquid. In a container, there is a liquid. What is the initial liquid volume? Let's say V1. Only think about the liquid. Don't think about the container. Only think about the liquid. There's a liquid. Its initial volume is V1. Liquid's initial volume is V1. Okay, no? Right? Liquid's initial volume is V1. And let's say your temperature of the liquid is increased by delta theta amount. Temperature increased by delta theta amount. Initial volume is V1. Temperature increased by delta theta amount. Only think about the liquid. Now, let's say now volume of the liquid is V2. If you measure the now volume, that is V2. If you measure the now volume, that is V2. Now volume is V2. If you want to find the final volume of the liquid V2 in terms of initial volume V1, remember, V2 means, remember the equation. Final volume of the liquid is equal to how much? Initial volume, inside the bracket 1 plus, volume expansivity is gamma, no? Gamma, it's real expansivity. Gamma is real expansivity in a liquid. Liquid gamma means real expansivity gamma. V2 final volume equals initial volume V1 plus 1 plus gamma. Delta theta, change in temperature. Simple story. This idea. Now we understood what is real expansion. And we understood what is apparent expansion. No? We know what is real expansion, what is apparent expansion idea also, we got the idea. If you want to find the real expansion, real increase in volume is the equation. V gamma delta theta, gamma is going to be the real expansivity. Let's say if you want to find the final volume of the liquid in terms of initial volume of the liquid, the equation is pretty much similar. Similar to previous stories. No? Again, this idea. Clear, no? This idea is clear. Theory point number 4, if you want to find the final volume of the liquid in terms of initial volume of the liquid, is the equation. Right, okay, so if I want to find only the apparent expansion, normally they ask apparent expansion story in a question. If they will tell, now you can identify. In a question, if they mention a liquid is completely filling the container, then they can ask apparent expansion ideas. Remember? In a question, if the liquid is completely filling the container, then they can ask apparent expansion story. So if I only want to find the apparent expansion of the liquid, right? The expansion of liquid which is visible to our eye. If I want to find the apparent expansion, the expansion of the liquid which is visible to our eye, how we can find the apparent expansion? Are there an equation? Yes, that's an equation. If you want to find this apparent expansion of liquid volume, remember apparent expansion story. Remember next point, theory point number 5. Time is 9:15. Apparent expansion of liquid. Theory point number 5. Apparent expansion of a liquid. Next theory point is apparent expansion. Right? Apparent expansion means what? The increase in volume of the liquid which is visible to our eye. Increase in liquid volume which is visible to our eye. If not O from liquid volume, apparent expansion. Apparent expansion equations, remember, apparent expansion is the overall content, not a theory class. In the theory class, we talk this story for one full day, okay? Right, see, I started this session, I think started at 7:45. Within 1.5 hour, 8:45, within 1.5 hour, I covered solid liquid gas expansion. Then I'm going to cover liquid expansion also. It's a kind of revision class, but you don't worry about that. All the points include. Just go and try. You can try all the past papers. Trust me. Some additional points are important. I will teach in passive stories, but it's the oral core. People who know the theory, they know it's the oral core. Okay. Apparent expansion. Apparent expansion stories. Apparent expansion ideas. Right. The equation is, remember, delta V. Apparent expansion is also delta V. Normally delta V, we write down capital R like that. Apparent expansion, if not we are calling it as relative expansion. Apparent expansion, if not we are calling it as relative expansion. Therefore capital R means relative. Apparent expansion, if not we are calling it as relative. Relative expansion. Relative expansion. That is what, again, same story. Initial volume of the liquid is V. Remember, apparent expansivity gamma R. If relative expansivity gamma R. Apparent expansivity, if not relative expansivity, into change in temperature. These equations are very similar, no? These equations are very similar. Similar equations. So you can easily remember these stories. And then finally, what is gamma? So gamma R is relative expansivity, if not apparent expansivity. Relative, if not apparent expansivity. Relative, if not apparent. Relative, if not apparent. Relative, if not apparent expansivity. Relative, if not apparent expansivity. Expansivity. So the units of gamma R is also same as per Celsius per Kelvin. Gamma R units also per Celsius, remember, per Kelvin. Right? Okay. Right, that's it, no? That's it. So if I summarize it, liquid expansion. Now, first point we want to remember is generally liquids have a fixed volume, but they don't have a fixed shape. That point is okay. The second theory point is, remember, when you consider equal amount of solid and liquid, and if you increase their temperature by same amount, generally liquid expand more than the solid. For an example, if you go to theory point number 3, so let's consider a liquid completely filled in a container. Then let's say now initial volume of the liquid also, initial volume of the liquid and initial volume of the container both are capital V and both at same temperature theta 1. And if you increase the temperature by delta theta amount, we realize since liquid expands more than the solid, some amount of liquid will overflow. Right, then if we check the real overall, if I check the overall expansion of the container, that is this volume, overall expansion of the container is corresponding to this volume, and if I find the real actual volume expansion of the liquid, volume corresponding to this volume plus overflow liquid volume, both together, total volume, actual volume is the real expansion, but the expansion of the liquid we can see. The expansion of the liquid which we can see is apparent expansion story. Then if you want to find the real expansion, total volume of the expansion, this equation. Relationship between final liquid volume and initial liquid volume is this equation. Then if you want to find the apparent expansion, this equation. That's it. Then theory point number 6 is very important. Remember, this is somewhat important. This part is somewhat important. Theory point number 6. Right, this is important. Theory point number 6 is important. All the points are important only. The theory point number 6. This is important point. Look here. Theory point number 6. Okay. Remember that means the real. That means look here. Real. If I want to find the total expansion of the liquid, real expansion of the liquid, I want to find this volume plus this volume. No. If I want to find the, look here, if I want to find the real expansion, remember, if I want to find the real expansion, remember, simple story, the real expansion of the liquid, that is equal to what? Real expansion of the liquid equals to what? It equals to this volume of the liquid plus this volume of the liquid. We know what is this volume. So this volume is apparent expansion. The real expansion is this volume plus this volume. This volume is apparent expansion. So apparent expansion of the liquid, apparent expansion of the liquid plus. So okay, the real expansion is this volume plus this volume. This is apparent expansion. What is this volume? This volume belongs to this volume. No, this volume is what? Expansion of the container. Remember, real expansion equals apparent expansion plus expansion of the container. Expansion of the container. You must remember the equation. Expansion of the container. Very important equation. Container. Put in your mind. From this equation, I don't do the derivation. We can obtain the relationship between real expansivity, apparent expansivity, and volume expansivity of the container. Right, let's say volume expansion of the container is gamma something. If let's say linear expansivity of the container is alpha. Let's say the linear expansivity of the container is alpha. Look here the story. Nice equation you want to remember. Nice equation you want to remember. The story is nice. Remember the story. This to remember, very nice story. Very nice story. Okay, once again, this content is enough more than, okay. You know, I can teach theory by conducting for long hours, and I can teach everything by briefing into a very small session. But still, I know that people who are listening to this discussion, anyone at any level can understand. Remember, this equation is very important equation. Remember, real expansivity gamma. Okay, real expansivity gamma, remember, that is equal to apparent expansivity gamma r, if relative expansivity gamma r plus volume expansivity of the container. Remember, volume, solid, no? Container is basically a solid. Volume expansivity of a container. Remember, normally for a solid volume expansivity we learned today, that is 3 alpha, no? Volume expansivity of a solid is 3 into linear expansivity of the solid, no? Therefore, 3 alpha, you must learn by heart this equation also. Real expansivity equals apparent expansivity for relative expansivity plus 3 into linear expansivity of the container. Write down. Yeah, what is alpha? Alpha means, remember, linear expansivity of the solid container. Story, nice story. Nice story. Nice story. Beautiful. Done, no? Done, okay. This is the overall core regarding liquid expansion. This is the overall core regarding liquid expansion. Now I will teach you 2 more points. Theory point 6 also done. Theory point 7, another point. Then overall idea is finished. I will teach you another 2 points. I will teach you another 2 points. Next 2 points. Next 2 points. Now you want to understand, okay, next point is, remember, right, so now next theory point is I erase this part, no? Better if I erase this part. We don't have space, no? Okay, next theory point, remember this theory point. This theory point. So now, okay, right, we understand, so in a liquid, we understand theory point, this is important theory point, number 6 important theory point. So we understand in a liquid undergoes expansion. So if a liquid undergoes expansion, we understand, okay. So we understand, look here. Theory point number 7, no? Number 7. Number 7, we understand, okay. Okay, so now just consider liquid, that's a liquid. Let's say now, initially at theta1 temperature, let's say theta1 temperature, volume of the liquid is V1 and mass of the liquid, let's say simple m, and density of the liquid is, let's say rho. Density is rho. At theta1 temperature, density of the liquid is rho 1 something. So we know that when during an expansion, we know mass remains same, mass does not change, but we know that when volume expands, when volume changes, during expansion or contraction, when volume changes, definitely density also changes. I can explain why, but it becomes a theory class, no? If I explain, if according to the density equals mass or volume, you can think, right? If I explain every point, it becomes a theory point, no? It becomes a theory class, no? Therefore, remember, if you consider a certain volume of a liquid, it has a certain mass, no? Therefore, due to an expansion, mass does not change. But what happens is, when the volume changes, density changes. That story. Same mass, but now volume is V2. Therefore, now density is rho 2. Now temperature theta 2. Change in temperature, if not increase in temperature, is what? Increase in temperature is what? That is delta theta. Increase in temperature is what? That is delta theta. Okay. Then remember the first point is, remember here, first point is mass constant. Mass constant. Therefore, when volume changes, density changes. That idea. Clear, no? Volume changes, we all know that density changes. You know that if I can explain, become a theory class, no? Okay, no, I don't want to explain, no mood of explaining. Density changes. In the past session, I will explain some stories. Density changes. For example, remember small point, when the volume is increasing, what will happen to the density? Remember, when the volume is increasing, for an example, density is decreasing. When the volume is increasing, remember, density is decreasing. When the volume decreases, density is increasing. That is the idea. Then they can ask you, they have asked you in the questions, essay questions and all, if let's say now at theta 1 temperature, density is rho 1. Now temperature increased by delta theta amount. Now density of the liquid is rho 2. They will ask you an equation linked with rho 2 and rho 1. Final density and initial density. So in that case, we all know that there are two ways. Remember, rho 2. Final density equals, remember, initial density is rho 1 over 1 plus volume expansivity of the real expansivity of the liquid delta theta is the equation. Final density of the liquid equals initial density over 1 plus gamma delta theta. Okay, this idea is the equation you want to remember. Remember this equation. And also remember now, to shorten sometimes, now this is the right equation, but sometimes having a denominator, this value makes the simplification complex. Therefore, what we do, we are modifying this equation and we are deriving an equation like this. We are modifying this equation and we can write down final density equals how much? Initial density 1 minus gamma delta theta. right? Don't you misunderstand. Now this equation is during an expansion. During an expansion of a liquid, if you want to find the final density, the actual equation is rho 2, final density equals initial density over 1 over gamma delta theta. But to make the simplification easy, you can do some modifications. Then you can convert this equation to this equation. Theory classes we prove these ideas, but in this revision class we don't prove those stories. But you want to understand, so this is for an expansion. If it is for a contraction, if the volume undergoes contraction, in that case here it must be 1 minus, no? It must be 1 minus, here plus. For a volume contraction, rho 2 equals rho 1, 1 minus gamma delta theta. Then here rho 2 equals rho 1, 1 plus story, that idea. This is the overall summary. Overall summary regarding the liquid expansion. Liquid expansion. Then there is some special point they talk about water. There is some kind of special characteristic in the water. That is what we call as anomalous expansion. In a water, normally we all know that when temperature increases, volume increases. As a result, density is decreasing. But when you consider this water, at a certain temperature range, water behaves something abnormally. That story, we have a past paper question today to discuss. In that past paper question, I will give a small brief, not that much explaining. I will give a small brief about that point also. Then you can revise that point also. This is the overall content regarding the solid expansion done. Then liquid expansion overall content is very clear. Summarized within that given time. I summarized every important point without skipping any single point. I summarized all theory points. Now the time is to do questions. We will talk about gas laws. We'll talk about gas laws. We start the class at 7:30, but we started at 7:45. No, 8:45, 9:35, 9:35. 9:35. What we can take a small break and come. We can take a small break and come. Time is 9:32. 9:32. We can come at 9:42. Come at 9:45. Take a break and come at 9:45. Then gas expansion. Then electric field theory point. Electric field intensity stories revising once again. If you have time, I will start fluid dynamic revision also once again. Okay, take your break and come. Come at 9:45 something. 9:45 something. I will come for sure before 9:50. Come at 9:45 something. 9:46, 9:47. Come at. Right, okay. Okay, no. Then solid expansion theories, solid expansion theories, liquid expansion theories, everything done. Generally, in theory classes, we are taking around 3 weeks to complete the story, but we have taken less than 2 hours and we completed all the theory points. Definitely today, evening class, 6 p.m. class, you will definitely learn something lot, right? You can learn something lot. Okay, then next story is gas expansion ideas. But today I plan to do in the past paper class solid expansion, liquid expansion, gas expansion, and electric field intensity part. Past paper questions I plan to discuss. There are around more than 100 MCQs, but I'm not sure with that given time 6 to 12 a.m. also even I do the class. I don't know whether I can complete everything, but we'll try our best to complete those stories. Next week in our revision class, next Tuesday, we are planning. In heat remaining stories, calorimetry, conduction, convection, calorimetry, conduction, convection, and then electric field, electric potential, Gaussian theorem. Then that day pass paper story. And also next day, for in case if I can't do any mechanics revision part today, but next week revision class I will revise one mechanics revision parts, 1 or 2 mechanics parts also. That is the way. I think this is the best way that one can revise the theories and one can do. But for the revision people, especially this, I want to tell that this actually the revision class, no, the revision paper class. No? Revision means a kind of rapid, quick revision, right? For now, we can't provide a tute for the revision class. I can't provide a tute for that because we don't have time. I want to prepare a tute and it takes some time. Therefore, I don't provide a tute for the revision class. But definitely for the past papers, for the paper class, right? I told you I will provide a paper book which is including set of daily papers. Each paper there are 15 MCQs, and those MCQs are in each paper categorized into section wise as well as idea wise. And also I will give an idea book also, right? Some questions are there to get that idea. I will send an idea book also, right? And then we are sending full paper class, all the full papers and marking schemes. But for this week and next week, maximum manage it. By the next week, you will get the papers and all. Okay, right? Okay, that is the overall idea. Okay, we have 4 months. We have 4 months. And practical book, I will send for anyone, rapid revision students or anyone. I will send the practical tute for everyone. Practical tute to everyone. That story. Okay, no. Last story is gas laws. Gas laws. And also give a small feedback also. If you have some time, this revision is okay. You are expecting something else, then tell me. Let's see if I can do something in my end. I'll try to do something, right? The story. Now these 4 months, okay, I will tell some advices today evening class. Today Samma will come to the remaining stories also, gas laws ideas. Next section, gas laws. Gas laws theory ideas. Next section. Gas laws. That is basically the gas expansion. Solid expansion, liquid expansion, and gas expansion is we talk on the gas laws. Okay, only the brief. We all know gas pressure. I don't explain how gas pressure forms in a container. That story I don't explain. When there is a gas in a container, we know there is a gas pressure in the container. In theory classes, we learn and we prove that how gas pressure exerts in a container. But that is not compulsory, therefore we are denying that story. First theory point under gas laws. 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 Very simple stories are there. Okay, no? Right, okay. Now, the first theory point is just consider there is a gas. It can be any gas. It can be hydrogen, oxygen, nitrogen, whatever in a container. Just consider not a theory point. Okay, it's a theory point. A small ideas. Okay, small idea. Okay, idea. Okay. Look here. Now there is a. Okay. Theory point number one. Theory point number one. Small idea. The idea is just consider there is a container. There is a container, there is a gas inside a container. It's a gas. There is a gas. Right, okay. Clear? Okay. Now the gas particles, it can be any gas. Okay, no? Right, okay, any gas. Remember, any point in the gas container, gas pressure is same. Okay? Remember, when you consider any point capital A, point capital B, point capital C, remember gas pressure at any point is same. Right? Gas pressure at any point is same. PA, PB, PC. And next point, remember, when you insert a gas into a container, remember, if the container is fully closed container, gas obtains entire volume of the container. The gas is completed in a container, gas obtains entire volume of the container. Therefore, remember, hereafter we consider volume of the gas as container volume. Whatever the volume of the container is the gas volume. The gas volume. Right? Next theory point is gas volume is always the container volume. Gas volume is always the container volume. This idea we know, basic idea. Container volume. Pressure at any point in a container. Pressure at any point in the gas in a container is same. Gas volume is the container volume. Container volume. This idea is okay, no? This idea is okay. This idea is okay. Right. Now we'll talk about Boyle's law. Basically, under Boyle's law, Charles law, pressure law, combined gas law, ideal gas equation, what we do is actually to analyze the characteristics of gas, we talk some parameters are dominant. For example, pressure, and then the volume, temperature, they are dominant people. So basically, under each law, we are going to talk the variation of one parameter relative to other parameter. That is what we talk under each law. I don't go deep and I don't explain. The first theory point, the second theory point is Boyle's law. Second theory point is Boyle's law. Second theory point is Boyle's law. Second theory point, Boyle's law. Theory point number 2. Okay? Theory point number 2, Boyle's law. The 100% effectiveness you can get by doing this paper class, okay? Then only you get the 100% effectiveness. If you are a revision student, you get the 100% efficiency if you join with the paper class, okay? Theory point number 2. Number 2. Boyle's law. Boyle's law. Boyle's law. Give me 1 second. 1 second. Somehow want to finish electric field story. Also time is 10 o'clock. We have 2 hours to go. We have 2 hours to go. Till now class is very effective according to my perspective. Till now the session is very effective. Right? Somehow we want to complete electric field story also somehow. That's our target. That's our target. That's our target. That's our target. Right, okay. Boyle's law. Remember, Boyle's law means Boyle's law. What is the idea? We are maintaining now in a gas sample. If you consider a certain gas sample, mass of the gas sample is a constant, no? The mass remains same. If you maintain mass, and temperature of the gas sample constant. If you consider mass and the temperature, if you maintain constant, mass and temperature of the gas sample remains constant, then we learned pressure is inversely proportional to the volume, right? Pressure is inversely proportional to the volume. That means, what is the idea? In a gas, if the mass and temperature remains constant, when you increase the volume, what will happen to the pressure? Pressure is decreasing, right? Then from this proportionality we can obtain the equation. Remember, right? Pressure equals K over V. That means pressure into volume is also constant, right? If you equal pressure equals K over V, that means remember pressure into volume is always a constant. Is the Boyle's law always a constant? Right, I do the session. Right, I'm doing the session. Pressure into volume is always a constant. Right? You write down pressure, volume. But normally remember any law, Boyle's law, Charles' law, pressure law, we apply for two states of the gas. And if a gas is at state 1, pressure is P1, volume is V1. If the same mass at same temperature, if the gas is at a different state, pressure is P2, volume is V2. Then P1 V1 equals P2 V2. That is a very popular equation. Normally, when you are applying Boyle's law for a question, we are applying not PV equals K. This one only, but we are applying P1 V1 equals P2 V2 equation. Right? P1 V1 equals. In theory class, I am going bit deep, but revision class, no need to go that level. P1 V1 equals P2 V2. Right? Okay. This idea. Clear? Clear idea. It's the Boyle's law. Right? Idea is okay, clear, simple idea. If you want, you can draw some graphs, but graph parts are not necessary, no? If you go with some parts, we can go from some parts. But drawing graph part is not that much important, but we'll do some graphs. Okay, fine. I will draw some parts. Right, okay, if I draw some parts, okay, no need, but it's okay. If I draw the variation of pressure with the volume, I'll draw some parts. It's okay. I'll draw some graphs. Let's say y-axis pressure and x-axis volume. How would be the graph going to be? I don't show that. I draw directly a graph like this. When the volume increases, pressure decreasing. This idea. Then, if I do the graph, pressure versus 1 over V. Graph. 1 over V. In that case, we are getting a graph. Pressure equals 1 over V means a graph like this. You guys think why? But we all know that. Next graph is pressure into volume. Over pressure into volume versus volume, no? That graph. Okay, only that graph. Then we can talk about next theory point, Charles' law. Okay, it's more than enough. This idea is more than enough. I will draw one more graph. Then we'll go to next theory point. Remember, this is a kind of revision, not theory class. It's not a theory class. But remember, from this point, from this theory point, you can do any question. Trust me. Can do any question. The next graph, if I do the next graph, let's say now the y-axis is pressure into volume. Remember, pressure into volume for a given gas at a certain temperature is always a constant. Therefore, remember, pressure into volume versus volume of pressure does not change, remains constant. Remains constant, this idea we learnt. Okay, some ideas. And now theory point number 3, Charles law. Theory point number 3, Charles law. Okay. Theory point number 3, Charles law. Next story. Next story. Next story. Next story. Theory point number 3, Charles law. Number 3, Charles law. Charles law. Charles law. Now idea. Now Charles law says that Charles law says this idea. Charles law explains right. Charles law explains for a given gas mass, if the pressure of the gas remains constant, for a given gas mass, the pressure remains constant. The pressure remains constant. Mass and pressure remains constant. Okay. Then what can you say about the volume? Volume is directly proportional to the absolute temperature. Then Charles said that for a given gas, if you maintain pressure constant, volume of the gas directly proportional to the volume of the gas is directly proportional to the absolute temperature. Remember, absolute temperature means, remember, that is temperature measured in kelvins. Right, this one is what? Absolute temperature. Absolute temperature. Absolute temperature. Temperature. Remember, that is temperature measured in kelvins. Okay, temperature measured in kelvins. Then the Charles law equations, remember, V over T. If I equal it, V equals constant capital K into T. If you substitute V over capital T, that is always a constant. This is the Charles law. If I apply for two different states this Charles law, V1 over T1 equals V2 over T2. So V1 over T1, that is equal to what? V2 over T2. V2 over T2. This idea. You must remember this equation. This equation. Then Boyle's law, Charles law idea is clear. Idea is clear. Idea is clear. Right. So then in Charles law story also we can draw some graphs. We can draw some graphs. Okay. I will draw the two graphs, but I don't go deep and explain. If you draw the variation of volume with the absolute temperature, if you draw the variation of the volume with the absolute temperature, then the graph, let's say y-axis is going to be your volume, x-axis is going to be the what? Absolute temperature. That means temperature measured in kelvins. Okay, kelvins. Then your graph is, remember, y equals mx graph. In case if you draw the variation of the volume of the gas respective to the temperature measured in Celsius, the next graph, the next graph, okay, y-axis volume of the gas, x-axis temperature only. But this temperature is measured in Celsius. In that case, we learned, if you can remember the graph, temperature measured in Celsius graph is a graph like this. A graph like this. This graph we learned, okay, some kind of ideas. Some ideas, okay, some ideas, right? Okay, this content is enough. In doing papers, past papers, I will revise all the theory points, all the important points in past papers. Theory point, then we talked about theory point number 1, point number 2 is Boyle's law, point number 3 is Charles' law, idea is clear. Then we talk about theory point number 4, that is special law. Theory point number 4, that is special law. Theory point number 4, that is special law. Theory point number 4 is special law. Theory point number 4, that is going to be the pressure law. Pressure law. Pressure law. Now same idea. Under pressure law, they are telling in Boyle's law we maintain mass and the temperature constant. Charles' law we maintain mass and the pressure constant. In pressure law we are maintaining in a gas sample, if you maintain mass and the volume of the gas sample constant. If you maintain mass and the volume of the gas sample constant, volume constant, then we know that pressure of the gas is directly proportional to the absolute temperature. Pressure of the gas sample is directly proportional to the absolute temperature. Okay, no? Then from this proportionality you can write down pressure over temperature, pressure over absolute temperature, that is going to be a constant, that's going to be a constant. Then P1 over T1, that is going to be equal to P2 T2. T2, this idea, clearly, simple stories. Even though we take time and we explain the theories for a long time, but when it comes to the question application, the content is very small. So we can bring entire that section's content into one single whiteboard. The content is very small. Okay, no? Then in this story also we can draw some graphs, variation of pressure with the temperature. If you want, we can draw the graph. I draw that graph. If I draw that graph, variation of pressure with the temperature, absolute temperature. Temperature measured in kelvins. Variation of the pressure with the absolute temperature. Okay. That graph is temperature measured in kelvins. Then also we are getting graph y equals ms graph. And if I draw the pressure variation with the temperature measured in Celsius, in that story, y-axis pressure, x-axis temperature measured in kelvins. If I do the graph going to be like this. The graph is going to be like this. This is the graph. Simple, no? Right, okay. Then these are the three main laws. Right, Boyle's law, Charles' law and pressure law. This is the oral content, oral summary. If you can know these points, you can do any question. Today you will understand. Now, next week onwards, you try the past paper questions first and then come to discussion. Then you can put your marks also. Then you get a time to try the questions by yourself also. Right, I am revising the theory briefly once again. In that week, you are doing daily past paper MCQs. In the next week, that day discussion. Also that every week, in addition to this past paper writing, one day we are writing full paper class. 5 paper writing and full discussion. Then this is more than enough. This is more than enough story. Right, okay. This idea also okay, no? This idea, right? The next story is, we are calling the next story as what? The next idea is we are calling combined gas law. A combined gas law, very simple. Now, under Boyle's law, Charles' law and pressure law, yeah, mass of the gas sample is always a constant. If you maintain mass of the gas sample constant only, we can talk about any law. But under Boyle's law, Charles' law and pressure law, you maintain only, in addition to the mass, you are maintaining only one variable constant, temperature constant. They are pressure constant, a volume constant. But under combined gas law equation, you are maintaining only mass constant. You are maintaining only mass constant. If the mass is constant, relationship between pressure, volume and temperature. Simple story. Theory point number 4 is combined gas law. Next idea. Next theory, I remember, combined gas law. Theory point number 5 is what? Theory point number 5, that is combined gas law. That is combined gas law. That is what? That is combined gas law. Combined gas law. Okay, combined gas law idea. Under combined gas law idea, the stories under combined gas law stories. Under combined gas law, we all know that mass of, if there is a gas sample having fixed mass constant, then we know that pressure into volume over absolute temperature always a constant. If we apply for two states of the same gas mass, P1 V1 over T1 equals P2 V2 T2. This is the whole idea. P2 V2 over capital T2. This is the whole idea. Is the whole idea. Overall idea. Right? Overall idea. Overall idea. This is the whole idea. Okay, no? Right? Okay. Then only we can talk about now. Boyle's law is done, Charles' law is done, pressure law is done, then combined gas theory is also clear. Very simple ideas. The summary, if you put into one single summary, it's very small story. The last story is, remember, now only we can talk about ideal gas equation. Ideal gas equation in theory classes, I showed how ideal gas equation comes and all, but no need to remember those things. Point number 5 is, this is the very important story. In case if someone forgets about Boyle's law, Charles' law, pressure law, combined gas law, also completely alright, you can try any question. You can do any gas law question by using only the ideal gas equation. Only the ideal gas equation. You can try any question. Try any question, ideal gas equation, next theory point, very important theory point. Ideal gas equation, very important point. Look here. Theory point number 6. Okay. Theory point number 6. Ideal gas equation. Can do any question. Ideal gas equation. Okay, ideal gas equation. Ideal gas equation. We all know that anyone can remember that story, PV equals nRT. Ideal gas equations, we all know that PV equals nRT, no? PV equals nRT equation. Pressure into volume equals, simple is number of moles, capital R is universal gas constant, capital T is absolute temperature, that means temperature measured in kelvins. This story done. Story done, no? Story done. Okay, here capital V means gas pressure, gas volume, number of moles, universal gas constant, capital is absolute temperature. Capital T, absolute temperature is important. Capital T here, absolute temperature. Absolute temperature measured in kelvins. That is important. That story. That story is done. Then 10-15 few hours to go for the story. Then if you can remember, I told you now, in addition to this equation, you want to remember, learn by heart, number of moles in a gas sample that is equal to, now we know what is number of moles in a gas sample. Right, there are two equations to find the number of moles. Remember, number of moles equals, remember, total mass of the gas sample over molar mass. Right? A capital M means write down total mass of the gas sample. Right? If there's a gas sample, let's say, there's a gas sample. There is a gas sample. Pressure is capital P, volume capital V, number of moles simple in, absolute temperature, that is capital T. Total mass simple lim, density of the gas is rho, and then universe Avogadro constant is capital N nil. Avogadro constant is capital N nil. Okay, number of molecules, total number of molecules capital N, and Avogadro constant is capital N nil. N nil. Right? Again, remember, number of moles means total gas mass over the molar mass. Molar mass capital M. Simple M is mass of the gas sample. Capital M molar mass. This equation you must remember. There is another equation to find the number of moles. That is, remember, number of moles equals to, remember, total number of molecules over Avogadro constant. Avogadro constant is capital N nil, no? Avogadro constant is capital N nil. Avogadro constant. And you must remember the value. Some exams, they don't give the Avogadro constant value. Remember, Avogadro constant value is, remember, 6.022 into 10 to the power 23 per mole. You all must remember Avogadro constant value is, remember, that is this capital NL value, remember, 6.022 into 10 to the power 23 per mole. Per mole, this value, you all must remember the story. Okay, no? Okay, right? Then from this equations, you can modify, if you want, what you can do, we can write down volume means what? We know the mass over volume is density equation. By using that equation, you can involve density in this equation. Likewise, we can do some modifications. Those stories I don't talk in here. When we are doing the papers, past papers today, you will understand how we can apply ideal gas equation, how we can link with other equations. That story we will talk in the today's paper class. In the content, overall summary. What you want to remember. If you can remember these theory points, then you can do any question. That's my point. That's my point. Okay, no? This idea is okay. This idea is okay. This idea is okay. This idea is okay. Right now, this idea is okay. Okay. Now time is 10:20, right? Now we start the class 7:45, 10:20. Now next story is, remember, next story is partial pressure law. Right, I want to teach you what is partial pressure law. Okay, Dalton's law of partial pressure. That is an important story. Dalton's law of partial pressure is important. The next theory point is, remember, Dalton's law of partial pressure. The next important story is, remember, Dalton's law of partial pressure. Theory point number 7. Right, theory point number 7. Theory point number 7, Dalton's law of partial pressure. Right, remember, Dalton's law of partial pressure. It's a very important theory point. Dalton's law of partial pressure. Dalton's law of partial pressure. Right, partial pressure. Dalton's law of partial pressure. Partial pressure, very important theory point. Right, very important theory point. Dalton's law of partial pressure. What is the idea? Now, let's say now, if there is a container, if there are many gases in a container, if that's a gas mixture. For an example, in a container, there is hydrogen, oxygen, nitrogen. At a certain temperature. In that container volume also capital V. Okay. In a fixed container volume, now there's a gas mixture. In a fixed container volume, this is a gas mixture. Okay. Right. Okay. In a fixed container volume, there's a gas mixture. Let's say there are 3 gases in that mixture. There are 3 gases in that mixture. And then Dalton told that let's say the volume of the gas container is capital V. Volume of the gas container, if not volume of the gas mixture, that is capital V. Container volume is capital V. And the same temperature is capital T. Volume is capital V and temperature capital T. Right? Okay. No? Then there is a gas mixture. Let's say there are 3 gases in that mixture. There are 3 gases in that mixture. There are 3 gases in that mixture. Okay, 3 gases. Right, red color gas, some kind of cross. And then blue color gas, some kind of dots. Blue color gas. Then there is another gas, for example, hydrogen, oxygen, nitrogen. Other one is a black color gas. Black color gas plus. Black color gas plus. Dalton told that. Dalton said that if you want to find the total gas pressure in the container under capital V volume and capital T temperature, If we want to find the total pressure of the gas mixture under capital V volume and capital T temperature, that is exactly equal to under same volume and temperature when you individually insert each gas. Under same volume and same temperature, if you individually insert each gas, the summation of the pressure produced by each gas going to be the total pressure of the gas mixture under same temperature and volume. Let's say now, if you only insert this red color gas in this container under same temperature volume, the pressure is capital P1. Pressure is capital P2. This gas under same temperature volume, pressure is capital P2. This one is a pressure capital P3. The total gas pressure is equal to how much? That is equal to P1 plus P2 plus P3. P1 plus P2 plus P3 idea. Very simple idea. Very simple idea, very clear. This theory also done. Done. No? This theory point also very clear, right? Okay, done. Theory idea done. Okay, nice story. The next idea. Some theory. These are put in your mind, right? Nowadays you can't be tired. Now even you're tired also, nothing to do. Keep on working. That's it, right? Next story. Then we'll talk about this. We will talk about kinetic theory of gases idea, right? And we want to understand about some theory points. I told you, right, in a gas mixture, I don't take that much of time to explain. But remember now, when there is a gas in a gas container, and there's a gas in a gas container, we know the gas molecules are moving in the random directions. Right, remember putting in your mind the summary. Put in your mind, when there's a gas in a container, give me 1 second. Just refer these things. Refer this entire story, refer it. Okay, next story. Right, next story. Give me 1 second. Next story. Just write the stories. Okay, then we can start within maximum 15 minutes. We can start the next last electric field theory idea. We can talk about electric field theory ideas also. Right, we can talk about electric field theory ideas also. Okay. Okay. Right, in the last electric field theory idea. Okay. Next story. Okay, right. Okay. And now I was explaining. Remember now. If there is a gas in a container, we know that this gas, just put in your mind this story. If you want, you can write in your notebook also important points. Generally, when you consider a gas in a container, these gas molecules, they move in random motions. Therefore, their velocities and direction are different. So when you try to find an average velocity of the gas molecules passing through a certain cross section, if you are trying to find the average velocity of those gas molecules passing through a certain cross section in the gas container, remember, the value becomes 0. But we all know these gas molecules are moving, therefore we can't have a 0 mean velocity. No? So if all the gas molecules, they are moving, having a velocity, we can't have an average velocity 0. Therefore what they have done is, to get a kind of average velocity for the gas molecules, they defined a velocity called mean scale velocity. That theory point idea. Next, theory point number 8. Mean scale velocity. Theory point number 8, mean scale velocity. Right, mean scale velocity. mean scalar velocity. Mean scalar velocity. The symbol matters. C2 bar root. C2 bar, no? C2 bar. The symbol is C2 bar. Symbol is C2 bar. Okay, C2 bar. Okay, mean scalar velocity. Mean scalar velocity. Okay. Now, what is mean scalar velocity? Remember, mean scalar velocity means when you consider if there are, let's say, if there are simple number of gas molecules in the container. If there are simple number of gas molecules in the container, right? Let's say there are simple number of gas molecules in the container, and their velocities are v1, v2, v3. Likewise, there are the velocities are if there are simple number of gas molecules in the container, the velocities are v1, v2, v3. Likewise, till vn. So the mean scalar velocity, remember the equation is this is not that much important. That is equal to what? v1 squared. v1 squared velocity of each molecule, v2 squared. Likewise, till vn. If there are simple number of gas molecules, till vn squared, you should divide by number of gas molecules. If there are simple number of gas molecules, divide by simple n. Simple n is this idea. And next we were talking about root mean scalar velocity. The root mean scalar velocity is this much. Root mean scalar velocity means the root of this value. Next idea is, remember, root mean scalar velocity. Root mean scalar velocity. Root mean scalar velocity means, remember, the symbol is, remember, C2 bar root. C2 bar root. The symbol is C2 bar root. Root mean scalar velocity. The symbol. Then the equation is, remember, C2 bar root. Root mean scalar velocity. That is equal, remember, this entire term's root value. v1 squared plus v2 squared plus till capital Vn squared divided by number of molecules simple length, entire root. Entire root. Just roughly put in your mind these stories. When you do questions, you'll understand more. But this is not that much relevant also. Right, okay. Okay, no. Again, very important theory points. Remember, kinetic gas equation. Like how ideal gas equation is very important. PV equals nRT is important. The next important equation that you are getting in the gas laws is, remember, kinetic what? Gas equation. Kinetic gas equation is very important. Kinetic gas equation very important. Theory point number 9. Theory point number 9, remember, kinetic gas equation. Right, theory point number 9. Kinetic gas equation. Very, very important theory point. What is kinetic gas equation? PV equals, remember, kinetic gas equation, remember, PV equals 1/3 simple M, capital N, C2 bar. Kinetic gas equation is what? PV equals 1/3 simple M, capital N, C2 bar. Right? PV equals 1/3 simple M, capital N, C2 bar. Okay? But remember now, please, just everyone define these values, define the symbols. People, they don't know the symbol mean what. P special is volume, but remember here simple M is not the mass of the gas sample. Wrong. Remember here simple M is not the mass of the gas sample. Here simple M is, remember, mass of one gas molecule. Remember here simple M is mass of one gas molecule. Right on here. Simple M means mass of one gas molecule. Here capital N means write down number of gas molecules. Capital N write down number of gas molecules. Simple M means mass of one gas molecule. Capital N is number of gas molecules. Capital N number of gas molecules. C2 bar means mean scalar velocity. Very, very important equation. Please mention kinetic gas equation. This is kinetic gas equation. This one is kinetic gas equation. Kinetic gas equation. Kinetic gas equation. Very, very important theory point. Very, very important theory point. Very, very important theory point. Very important. Very important theory point. Okay, no? Right, okay. Now, till now, I think today we talked about solid expansion, liquid expansion, gas laws, or revision. I think we took almost 3 hours close.
It almost three have a closer, and somehow I think all theory points we covered, no? But we'll see if there are any other important theory points on the gas laws. Any important theory points on the gas laws. We talked about Boyle's law, Charles' law, pressure law, combined gas law, ideal gas equation, these stories, Dalton's law of partial pressure idea, mean square velocity theory points roughly. We talked about the kinetic gas equation. And also there are two more equations. There are two more equations. I will tell you. This Rotminskian velocity equation, look here, there are some equations for Rotminskian velocity. Remember, Rotminskian velocity equation is, remember, 3 capital R into capital T over capital M. Rotminskian velocity equation is, remember, 3 universal gas constant, absolute temperature over molar mass. There's another equation of Rotminskian velocity, that is what? That is 3 capital P over rho. 3 capital P over rho, whole root. These equations are very important. Very important. Remember Rotminskian velocity equations. Is important. Is important. Is important. Is important. Is important. There is one last two equations, then everything is finished. There is one last two equations. There is one last two equations. Right. When there is a gas in a container, if you want to find the kinetic energy of that gas sample, if you want to find the kinetic energy, mean kinetic energy of that gas sample, right, there are two equations, remember, mean kinetic energy of a gas sample. Where can I write down? Now, where can I write down mean kinetic energy of a gas sample? We can write down any space here. Right, okay. Look here. Look here. Last theory point. Point number 10. Point number 10, last theory point. Point number 10. Theory point number 10, last theory point. Then done dusted entire story. Theory point number 10. Point number 10, story done dusted. Okay. Theory point number 10, look here. Theory point number 10, look here. If there is a gas sample in a gas container, if there is a gas sample in a container, if you want to find the total mean kinetic energy of that gas sample, the equation you must remember is, remember, capital E equals 3 over 2, right? Capital KT, right? The mean kinetic energy is how much? 3 over 2 capital KT. For the entire gas sample. Capital K is what? I will tell you capital K is, okay? Okay, right. Okay, this equation 3 over 2 capital KT. Capital K is a constant. Capital K is, remember, universal gas constant over Avogadro constant. N capital E, no? Capital K is, remember, universal gas constant. Capital K is what? Universal gas constant over N capital E, Avogadro constant. Right? Capital K is what? Universal gas constant capital R over Avogadro constant N capital E. Avogadro constant N capital E. Avogadro constant N capital E. This capital K is what we call as Boltzmann constant. If you can remember, this capital K is what we call as Boltzmann constant. Boltzmann constant. Right? What's my target? Write down here mean kinetic energy of a gas sample. Write down like this. Mean kinetic energy of a gas sample. That is equal to 3 over 2 KT. 3 over 2 KT. Okay, 3 over 2 KT. Okay. That story. Okay. Give me 1 second. That story. Give me 1 second. Just refer everything. Give me 1 second. Refer everything. Give me 1 second. Okay, I made a small mistake. This is 3 over 2. I made a small mistake here. Mean kinetic energy of an entire gas sample is, that is 3 over 2 nRT. Simple nRT, 3 over 2 nRT. I made a small mistake. Huh? 3 over 2 nRT. Okay, I made a small mistake here. For entire gas sample, mean kinetic energy is 3 over 2 nRT. 3 over 2 nRT. nRT. But if you want to find the kinetic energy of one gas molecule, for one gas molecule, mean kinetic energy of one gas molecule, that is 3 over 2, that is 3 over 2 kT, 3 over 2 kT, 3 over 2 kT, 3 over 2 kT, 3 over 2 nkt, no, 3 over 2 nkt. Okay, that is 3 over 2, that is 3 over 2 kT. Okay, yes, 3 over 2 kT. Yeah, 3 over 2 kT. Please write down for one gas molecule is 1. If you want to find the kinetic energy of one gas molecule, one molecule is 1 is for entire gas sample. Entire gas sample. What is K? This K is, as I explained already, K is Boltzmann constant. That K, well, remember, K is Boltzmann constant. K is Boltzmann constant. Write down somewhere else. K is Boltzmann constant. K is Boltzmann constant. That is, remember, Boltzmann constant is, remember, R over universal gas constant over Avogadro constant. Got it? This story. K is Boltzmann constant. Boltzmann constant. That's it. All the theories covered. Boltzmann constant. All the theories are covered. That's it. That's it. Nice, no? Entire story nice. Entire story nice, no? Very nice story, right? Okay. Now give me all a small thumb, right? I think we talked about genuinely. I think all the important theory points by covering A to Z properly. Important theory points, A to Z properly. I think we covered everything properly, no? I think we covered everything properly. I think we covered everything properly, right? We talked about solid expansion, liquid expansion, gas expansion. I think give me a small reply if everything is very clear. I think I revised everything within this given time, within this small time period. I think 7:30, 8:30, 9:30, 10:30. This small time period, we took a 15-minute break only. But within the 3 hours, we covered the main section. Normally, to complete this entire story in the theory class, we are taking more than 1 month. But we took within 3 hours and I revised everything. But very quickly, the real benefit you are getting of the story today evening session, passive session only, we are getting a nice stories there. Put a small reply, put a small thumb if all good. If all good, put a small thumb. Put a small thumb if all good. Put a small thumb if all good. Give me a small reply if everything is good. Give me a small thumb if everything is good. Now we can start electric field theory ideas. Nice, no? Nice story. Nice story, no? Nice story. Then, right, okay. Time is 10:45. 10:45. We can take a small break. Time is 10:41. No, come at 10:50. 10:52. Then maximum 11:30 only. Okay, take a break. Come at 10:50. Take a break and come. 10:50 something. 10:51 maybe. 10:51 maybe. 10:52 maybe. Take a break and come. Okay, right. Okay, the last story for today's story. Time is almost going to be 11. Target is completing, finish the class before 12 o'clock. That's our target. Electric field, Unit 6 electric field, very confusing lesson. But today we are doing past papers from electric field also. So then the idea, right. First, today we are talking about electric field intensity concepts. Okay. Uh, Even though we took time that much and we learned that lessons, but if you summarize into one single paper, the important points to be remembered is very less. But we have a lot to learn from the questions. That's the problem, right? We have a lot to learn from the questions. But theory-wise, the summary is very simple, very small summary. Next idea, electric field ideas. Okay. Now, electric field, we were talking lots of theory ideas, different stories. I start from the beginning. You know that normally when I explain something in a theory class, I don't just directly to the theory. No, I go from the base to the bottom to the top. No? But in our revision classes, we can't expect that level explanations. But what is important to do question that is only explained in the session. Okay. But nothing come beyond this summary idea. Okay, in your papers, nothing come beyond the summary idea. Okay. Last idea for the day, and today 6 p.m. we are starting the class. Last idea. Last idea. The last idea. The last idea. Okay. Stay focused, maximum 1 hour, then story finished. Unit 6 electric field theory points. Right, okay. Unit 6 electric field. Somehow we are completing entire syllabus once again within this 4 months with our best. Electric field idea. Electric field theory points. Electric field theory points. Okay, no? Right, okay. All right. Right. Now, we all want to know that what is electric charge. No, the first idea is electric charge. We all know that like mass, length, time, right? Like if you consider a substance, a material, they have a mass, they have volume, and they have a density. Likewise, remember the substances, the particles, they have a property called electric charge. Right? Electric charge. First theory point is understanding about electric charge. It's a kind of property that the particles have. Okay. First theory point is remember understanding electric charge. Right? Understanding electric charge. Okay. So then remember electric charge means remember electric charge. Electric charge, the symbol is capital Q. Electric charge, that is also the kind of property that particles have. Like mass, like density, volume. Electric charge is also the kind of property that particles have. Electric charge. Electric charge. The symbol is capital Q. Capital Q. Right? Okay. Okay, no. So then, how did you define electric charge? That definition is not that much relevant. Okay, the definition is not that much relevant. Okay, now give me 1 second. It's not that much important. It's not that much important. Okay. Right. Right. Okay. Look here. Now we learned in our universe there are two types of we know there are particles. They have a property called electric charge. Alright, remember based on the nature of the electric charge I told you, we can divide particles into two types of natures. Particles who are having this property called electric charge, based on that electric charge nature, we can divide all the particles into two types. One is positive electric charge type, other one is negative electric charge type. Therefore, we are calling positive electric charge, negative electric charge. Particle having positive electric charge, particle having negative electric charge. Right? Okay. Right, the unit to measure the electric charges, we all know that coulombs. Unit is coulombs. SI unit to measure the electric charges, we all know coulombs. Capital C coulombs. This idea we can remember coulombs. Coulomb. Electric charge, two categories: positive electric charge, negative electric charge. No. Electric charge of a particle, there are two types of electric charges. One is positive electric charge, particles having positive electric charge, and then particles having negative electric charge. They identified, for an example, if you give an example for a particle having positive electric charge, the best example is proton. No? The best example is proton. Right? The best example for a particle having negative electric charge, that is electron. Then we all know that. Does that mean that all the particles are either positive electric charged or negative electric charged? No. There are some particles which are neutral. Some particles, they don't have this property called electric charge. We are calling them as neutral. The best example for a neutral particle is neutron. Neutron does not have any overall electric charge. Therefore, neutron is a neutral one. Okay. Likewise, not only the example for positive, negative is not only electron and proton. You can tell any cation for positive charge particles. You can tell any anions for the negative charge particles. You can tell plenty of examples. Okay. Now, but mainly we are talking the stories in terms of electrons idea. Actually, electric field. The story we are entirely talking in terms of electron idea, right? Electron idea. Okay. So then we talked about, remember, the charge of an electron is what? We all know. The charge of an electron is, remember, that is 1.6 into, you must remember this value, you must learn by heart. Charge of an electron is, remember, that is equal to 1.6 into 10 to the power minus 19 coulombs. Right? Not only the charge of the electron, but also remember the charge of a proton also equal to 1.6 into 10 to the power minus 19 coulomb. Charge of a proton is same. Proton charge is same charge. Proton charge also, you can tell QP means proton charge. Charge of a proton is also same as 1.6 into 10 to the power minus 19 coulomb. But remember, electron or proton both are having electric charge, but their nature is opposite. That's why we are telling positive, negative. This theory is clear, no? Theory is clear. This theory idea is clear, ni? This theory idea is clear, right? This theory idea is clear, ni? Idea clear. Now what happens is, now when you consider objects, the next theory point, when you consider objects, now what happens is, when you rub the object to, we are telling some phenomena like conduction and induction. What happens is, if an electrons, now we know normally all our objects are under neutral condition. We all know objects are neutral condition. That means number of electrons and number of protons in that object is same. Therefore, we can tell the object's overall charge is, electric charge is zero, neutral. But what happens if the electrons are removed from that object? Then we tell that object is positively charged. Some idea. Summarily, I am telling. If there is a neutral object, if there is already a neutral object, if electrons are removed from the object, now this object becomes, now this object is having less number of electrons than the number of protons. Therefore, this object becomes positively charged. right? The next story is, let's say if there's a neutral object, if you supply electrons to this object, and now this object is having excess number of electrons than the protons. That means total negative charge is larger, total positive charge is smaller. Therefore, this entire object becomes negatively charged. Right? Negatively charged. This idea we know. Okay. And neutral means we all know that total number of negative charge and positive charge are same. That idea clear? And positively charged object, positively charged. Some stories. Time is 11 o'clock. A positively charged. Next idea is negatively charged. Negatively charged. Briefly explain negatively charged. Clear? Idea is clear. Generally, they found in the universe the smallest. If the particle having smallest magnitude for the electric charge is the electron. When they found in the universe, the particle having smallest electric charge, smallest magnitude of electric charge is the electron. Therefore, if you want to find any object's total charge, we can use this equation, very important equation, Q equals Ne. If you want to find the total charge of an object, that is equal to N into simple E. Charge of an electron, number of electrons in that object, Q equals Ne equation. Q equals Ne equation, next story. Q equals Ne equation, next story, theory point number 1. Right, electric charge, oral idea, summary, oral idea. Clear ni? Right, have an idea, right, clear ni? Idea is clear. Idea is clear ni? Right, okay, oral idea is clear. This overall idea is clear. This overall idea is clear, right? This overall idea is clear. Overall idea is clear, next story. Next story, okay? Now put a small thumb everyone, if till now everything is very clear. Right, till now everything is very clear, put a small thumb everyone. Put a small thumb, if all good. If all good, give me small response, if all good. If everything is okay, give me small response. Now I am summarizing, okay? If I start explaining, you know how long I took to explain electric field, no? I am summarizing as much as possible, right? I am summarizing as much as possible. All good, no? Okay? Right, I am summarizing everything, okay? Because we want to do lots of stories hereafter. Mainly past paper questions, that is the problem. Mainly past paper questions. That is the main story. Okay, no, all clear, no? All clear, right, okay. Maximum 1 hour, then today's session is very effective for me. I don't know how you experience, put a small WhatsApp reply, okay? Right, you all have my WhatsApp number, no? My WhatsApp number you all have, right? I will put here also if there are anyone watching newly for our stories, right? Put a small reply. All good, put a small reply. Next idea, right? Okay. Electric charge theory idea is very clear. Idea very clear, no? Very simple idea, right? Next idea. The next idea, theory point number 2. Theory point number 2, next idea is we'll talk about what is this electric field intensity. We understood particles having a property called electric charge, then blah blah blah. Okay, what is that electric field intensity? What is that electric field intensity then? What is that electric field intensity then? Next story. Next story. Want to finish now? Time up. Time up. What is then electric field intensity? Next story. Next story. Okay. Next story. Right, electric field intensity. Okay. Next theory idea, Coulomb, next theory idea. Right. The next theory idea. The next theory idea. Theory point number 2. Right, theory point number 2. Theory point number 2. What is this electric field intensity? Theory point, very important point. Theory point number 2. What is this electric field or electric field intensity? We'll understand electric field idea. That's better. Electric field idea. electric field, if not electric field intensity. Electric field intensity. Electric field intensity. The symbol is, we all know that capital E arrow, no? Electric field intensity means we all know that capital E arrow. It is capital E intensity, capital E arrow, electric field intensity. Now the next theory ideas, if I'm explaining. Next theory ideas. Now you get the 100% benefit of this rapid revision program if you join for the paper class, okay? Right, with me, if you should do the paper questions before and you should come for the discussion, then only you get the 100% effectiveness. Then there is no point, no? Right, okay. Next theory idea. Next theory idea. Right, okay. Okay. Now, what is electric field? I told you that electric field means, we all know. I explained briefly only, I'm telling you, okay? I don't take that much of time. Time is 11:10. Electric field. Electric field means, I told you, when you consider a particle having electric charge, around that particle there will be a kind of region formed. That region can produce forces on other charges. If you consider a particle, let's say there's a particle having electric charge plus Q. There's a particle, this particle is having electric charge plus Q. I told you around this particle there will be a region formed where, if not, that region can produce forces on electric charges. This electric charge creates its own region which can create forces on other electric charges. I draw that electric field in dotted dots, local dots. So I didn't understand what is electric field. Electric field means, remember, when you consider a particle, due to its electric charge, there will be a region formed around that charge which can create forces on other electric charges. Then the region which can produce electric forces on the charges we call as electric field. This region, this volume is we call as electric field. This region is we are calling as electric field. Idea is okay, understood. It's what we call as electric field. Idea is okay. But remember, this blue color electric field is produced by discharge. Therefore, don't ask. Remember, this electric field is produced by this charge, no, plus Q charge, no. Therefore, there won't be any electric forces exerting on this charge. Okay. The one who produces the electric field does not go. The one who produces the electric field does not undergo an electric force. Right? This guy only creating this field. Right? If there are other particles, like this, there are another particle, simple Q something. Then there will be electric forces on the simple Q. There will be electric forces acting on simple Q. There will be electric forces acting on simple Q. Very simple summary. Electric field is what? A region where forces can exert on particles having charges. What's electric field? Electric field means what? A region where forces exert on electric charges. For an example, if this blue color electric field is produced by plus capital Q charge, if you bring another different charge Q into the field, there will be electric forces exerting on this charge. But remember, the one who producing the electric field plus Q, no, does not undergo any electric force due to its own electric field. Due to this blue color electric field, there won't be any electric forces exert on this plus Q charge. Right? Who will undergo electric forces? The other particles, other charges. That idea is enough. Electric field is okay. Now we'll talk about electric field intensity. It's very important idea. Electric field intensity, remember, what is electric field intensity? The idea is very simple, right? Now, electric field intensity is very simple, right? In the electric field, if there's an electric field, at a point, when you keep plus 1 coulomb charge in the electric field, remember, electric field intensity idea, remember, okay? In the electric field, at a point, if you bring plus 1 coulomb charge, so we know if you bring any external charge to the electric field, if you bring +1 coulomb charge to the electric field, what will happen? There will be electric forces exert on +1 coulomb charge. Let's say the electric force exert on this +1 coulomb charge is Fe. My bad. We know that in the electric field, when you bring +1 coulomb charge, in an electric field, if you keep +1 coulomb charge, there will be electric forces exert on that charge. That electric force exert on +1 coulomb charge is what we call as electric field intensity. You understand? If you bring +1 coulomb charge into the electric field, the electric force on +1 coulomb charge is what we call as intensity. So remember, intensity means, remember, electric force on +1 coulomb charge. Intensity is what? Electric force on +1 coulomb charge. Electric force on +1 coulomb charge. +1 coulomb charge. Clear no? Right, okay. Then in case if the charge is capital Q, we'll learn the equation. Just consider in the electric field. In the electric field, now there is a charge that is capital Q. And if you know the electric field intensity, I told you, remember, that means, in the next story, okay, we understood what is electric field. Right, we understood this electric field. Okay, remember this, there is a +Q charge. There is a charge. Different points in the electric field, different points can have different electric field intensities. Okay, that story I will teach you in a while. Okay, right. Okay, what is electric field intensity? In the electric field, if you bring +1 coulomb charge, the electric force, that is okay. Then in that point, let's say if you know the electric field intensity, at a point, electric field intensity is capital E. They have given intensity at a point is capital E. Then the charge at that point is capital Q. And if you want to find the electric force, remember we learned the equation. The electric force acting on capital Q charge at a point having intensity capital E, so you will know that F equals EQ equation. Electric force equals electric field intensity into the F equals EQ. F equals EQ. F equals E, simple Q, F equals EQ equation. This equation we learned lastly. We learned these ideas, right? Okay. Right, this idea is okay. Idea clear. So then important points regarding electric field. Remember some stories. Remember now. So then, right, okay, understood what is electric field. Remember, electric field intensity is defined for a point in the electric field. Based on the scenario, remember, different points in the electric field can have different intensity values. Look here. I forgot to mention, remember, intensity is a vector. I forgot to mention here, electric field intensity is a vector. It's a vector. I will tell you how to find the direction of intensity. I will tell you. Remember, units of electric field intensity is what? That is what? Force per unit charge. Therefore, Newton per Coulomb. Newton per Coulomb is the unit to find the electric field intensity. Newton per Coulomb. Units of electric field intensity is Newton per Coulomb. The units of electric field intensity is Newton per Coulomb. Right, okay. Okay. That idea is okay. Please mark the stories. Understand what is electric charge, what is electric field intensity, what is electric field ideas. Write down the stories. Write the stories. Now, next idea is, remember, next theory idea. The next theory idea is, remember, next theory idea. Okay, the next theory idea, time is 11:20, won't stop the class now. We need the next theory idea, remember, next theory idea. Right, okay. Now we'll talk about electric field produced by a point positive charge +Q. Right? When you consider the electric field, theory point number 2 is okay, no? Now theory point number 2, we talked about what's electric field, and electric field intensity means that idea. Basically, electric force on 1 coulomb plus 1 coulomb charge is electric field intensity. Vector per coulomb, this equation is mattering. Then theory point number 3. Next theory point is, we'll try to understand how electric field intensity gonna vary for a point positive charge. Theory point number 3. Theory point number 3, remember this idea. This idea. We know that when there is now initially the space is empty, there was no any people in the space. Let's say now when you keep a point positive charge plus q, if you keep a point positive charge plus q, as I told you, this plus q charge produces an electric field around itself. This plus q charge produces an electric field around itself. I just draw some dots to represent the electric field around this point positive charge plus q. Okay, no, that is okay. That is okay. That is understandable. Okay. Now remember, if you want to find the magnitude, I told you, remember in this scenario, first important point is when you go point to point, remember point to point in this electric field, for an example, point capital E. For example, point capital E, point capital B, point capital C, different points have, remember, different electric field intensities. Point to point turning, different points in the electric field have different electric field intensities. Okay, write down that point. Different points have different electric field intensities. Point to point, right? Point to point intensity varies. Point to point intensity varies. Intensity varies. Point to point intensity varies. First point. And also remember, when you go far from this plus capital Q charge, that intensity is reducing. If you are going far from the plus Q charge, that intensity, electric field intensity is reducing. Let's say if you want to find the intensity at a point, let's say there is a point like point capital E. If you want to find the intensity at a point which is simple r distance far from point capital E, it is simple r distance far from point capital E. If you want to find the intensity at a point which is simple r far from point capital Q. If you want to find the intensity at a point capital E which is simple r far from this plus Q charge, the equation to find the intensity is learned by heart. Intensity equals, remember, 1 over 4 pi epsilon. I will tell you what is epsilon. It's a constant which depends on the electric properties of the material. I will tell you. I will teach you, don't worry. 1 over epsilon, capital Q over R squared. Capital Q over R squared. Capital Q over R squared, this idea. Remember here capital, this is epsilon. 4 pi is 3.14. If not 207, here epsilon is, remember, it's we call as a constant which depends on the properties of the medium. Sometimes this electric field form in the air, in the water, in the any other medium. Therefore, this epsilon is a constant which depends on the properties, electric properties of the medium. We are calling it as permittivity. Epsilon we are calling it as permittivity. Epsilon we are calling it as permittivity. Epsilon just roughly mentioned. Now today we are doing some questions. Electric permittivity. Remember, it depends on this permittivity depends on the electric properties of the medium. Electric properties of the medium. Okay, right? Okay. Then so now theory point number 3 is electric field intensity produced by a point positive charge. Electric field intensity produced by a point positive charge. The equation is 1 over 4 5 epsilon capital Q over R squared. That means larger the distance. When you go far from the point charge, what can you say about the electric field intensity? Decreasing. Therefore, remember, if you go far from the, right? If you go when R increases, that electric field intensity is decreasing. Got it? Okay. Right? Okay. Till now, theory point number 1, 2, 3 done. Then from these theory points, what we learned, a small summary. Electric charge idea is okay. Now, electric field is a kind of region which can produce forces on electric charges. And Electric field intensity means in that electric field, different points have different electric field intensity. Electric field intensity at a point means at that point, if you keep +1 coulomb charge, the electric force is what we call as electric field intensity. Basically, electric field intensity is the electric force per unit charge. That idea. And next theory point number 4 is very important theory point, Coulomb's law. Coulomb's law. Coulomb's law. Newton's law of Coulomb. Next story. Theory point number 4. These are the important summary, okay? Summary points. Theory point number 4. Theory point number 4. Theory point number 4. Right, Newton's law, Coulomb's law, no? Next idea. Next idea, Coulomb's law. Next idea, Coulomb's law. Next idea, Coulomb's law. Okay. Now Coulomb's law idea, right? Coulomb's law idea. Okay. Right, Coulomb's law idea. Right, okay. Coulomb's law idea. Okay. Coulomb's law idea, right. Okay, Coulomb's law idea. Okay. Right, okay. Before going to Coulomb's law story, we'll talk about, sir, let's consider now, okay, right, we understood when there's a point positive charge, there will be electric field around this point positive charge. To find the electric field intensity at a point, this equation we can apply. That is okay, sir. But how do you find the direction of electric field intensity? You told that electric field intensity is a vector, no? Remember, if it is a point positive charge, remember, look here, direction of intensity, look here, direction of intensity, direction of intensities. If it is a point positive charge, if it is a point positive charge, look here, a point positive charge, let's say if you select some points, point capital A somewhere here, point capital B somewhere here, point capital C. Remember, the direction of, if it is a point positive charge, just keep +1 coulomb charge at point capital E. It's a point positive charge. You want to find the direction of electric field intensity at point capital ABC. If you keep +1 coulomb charge here, plus and plus. Normally, positive charges we will learn, they repel each other, no? They repel each other. Okay? Always remember, if it is, if you want to find the intensities at any point in the electric field produced by a point positive charge, always away from the positive charge. Intensity direction is always away from the point positive charge. Away from the point positive charge, intensity direction. At point capital B, always away from the point positive charge. Always away. Time up, want to stop the class now. AB. Intensity at point capital C also always away from the point positive charge. Always away. Always away from the point positive charge. Always away from the point positive charge. Okay, no? At point capital C. AC. But if it is a negative charge, if the electric field is produced by a negative charge, if the electric field is produced by a point negative charge, let's say point capital A, point capital B, point capital C, intensities we want to find. Remember, they are always towards the negative charge. Electric field intensities at point capital A, B, C are towards the negative charge. Negative charge, AC, EB. Electric field intensity at point capital A, EA, towards negative charge. That idea also important. So that means for a point positive charge, intensity directions are away from the point positive charge, intensity directions are towards the point negative charge. Idea is clear. Then next point is how to find the resultant electric field intensity at a point if there are multiple electric charges in that region. Till now we talked about, we found electric field intensity if there is only one electric charge at a point. No. If there is, now when there is only one electric charge plus Q, if you want to find the intensity at point capital A, yes, you can use this equation. But if there are many charges and at a point, if you want to find the resultant electric field intensity, that idea. Then resultant electric field intensity idea, theory point number 5. Theory point number 5, resultant electric field intensity. Resultant electric field intensity, next idea. Right, resultant electric field intensity idea. Look here. Resultant electric field intensity. Resultant electric field intensity, capital E. Same idea. Let's say now there are three charges, for example. This is charge plus Q1. If it does Q1, this charge is, let's say, Q2, this charge Q3. And you want to find the intensity at somewhere here, point capital E. Then we all know that just think intensity. It's a positive charge, think like positive charge away, no? Intensity at point capital A only by Q1 charges, no? Away, no? That is E1. That is E1. If you want to find the intensity at point capital A by Q2 charge, that is E2. Just think like that, E2. Intensity at point capital A by Q3 charge, that is E3. E3. So you can individually consider each charge in the field and mark E1, E2, E3. Then you want to obtain the vector sum. You can't add E1 plus E2 plus E3. You want to get the vector sum. To find result intensity, get the vector sum. This story you guys know, vector sum. Get the vector sum. Vector sum of E1, E2 and E3. Right? This idea okay. When we do the question today, you will understand the story more. Next one is, the next and most important story is Coulomb's law, no? Theory point number 6. Next important point is theory point number 6, Coulomb's law idea. Theory point number 6 is Coulomb's law idea, no? Theory point number 6. Theory point number 6, Coulomb's law idea. Coulomb's law idea. Okay, Coulomb's law idea. Give me 1 second. Keep on writing this idea. Maximum 50 minutes. We can finish the story today. I think we learned a lot today. We learned a lot. It's good, nice. We learned a lot today. Last theory point. Okay. The last theory point, Coulomb's law story. Coulomb's law. Remember, Coulomb's law says, simple story, Coulomb's law. Very important theory point, Coulomb's law idea. Look here, stay focused and learn. Stay focused till the class finishes. Stay focused. That's very important. Stay focused. Coulomb's law idea. Let's say that it says that now when there are, if you consider two electric charges, two particles having electric charge. Let's say now there is a positive charge, and there are two positive charges. When you consider there are two positive charges having different electric charges. Let's say Q1, Q2. There are two positive charges having different electric charge. Let's say Q1, Q2. Let's say capital Q, simple Q. This one having an electric charge, capital Q, simple Q. The gap between them is simple R. Remember, there will be electric forces acting on them, action-reaction forces. But remember, same type, no homogeneous electric charge, no same type, no positive, no. Therefore, there are repulsive electric forces acting on them. The electric forces acting on them are repulsive. Repulsive electric forces acting on them. Repulsive electric forces acting on them, Fe. Right, repulsive electric forces acting on them, Fe. Also, when you consider same, there are two negative charges. If there are two negative charges, if there are two negative charges, if there are two negative charges in this story also, minus minus, negative minus minus. This one charge is plus capital, this one charge is capital Q, and this one's electric charge is, let's say, simple Q. The gap between them is simple R. There are two particles having a negative electric charge. Magnitudes are capital Q and simple Q. Then also same type, no, negative, negative, no. Again, there are repulsive electric forces. There are repulsive electric forces, Fe, 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 Fe. But when you consider particles having a different electric charge, that means positive electric charge and negative electric charge. Positive electric charge and negative electric charge. Positive electric charge and negative electric charge. Negative electric charge. The charges are plus Q minus Q. The charges are, the magnitude of the charges are capital Q and simple Q only. The magnitudes of the charges are capital Q and simple Q only. Then they have a kind of electric attractive forces. Right, this is positive, negative electric charge. They have electric attractive forces, Fe, Fe. Then Coulomb said that this attractive force that is equal to 1 over 4 pi epsilon. 1 over 4 pi epsilon. Remember, capital Q, simple Q over distance between them r squared, r squared. You must learn by heart. Newton's Coulomb's law. Coulomb's law said that this attractive or repulsive forces equal to 1 over 4 pi epsilon capital Q simple Q r squared. You must learn by this equation. You must learn by heart this equation, Coulomb's law. Coulomb's law. Coulomb's law. Now this is the overall idea. Now we can talk about some graphs and all. We can talk about some graphs and all, but this content is enough, no? To do today's questions, this content more than enough. Okay. Anything else? Any important point? These are the core important points. See now, summary is very small. But when doing questions, no, there are different types of questions. Okay. So today we took a long time and but put in your mind roughly this value. Normally, if the atmosphere is vacuum, if you want to find the permittivity, remember generally, if you want this 1 over 4 pi epsilon value is, remember, 9 into 10 to the power 9, this value. Okay? Right? This story is enough. Enough, no? This idea is enough. Yes, electric field line story is there, then potential ideas, not today. Okay. Time is 11, almost 11:40. Right, listen. Listen, this is the way. Now within 4 months, sometimes not even 4 months, sometimes 3.5 months, because till the last moment we can't do a revision class, no. Within this 3.5 months, revising every theory point properly, you can understand, we all can sense the story, no. Just imagine for 2.5 years thing that we are doing in our theory class, and within 3.5 months completing again entire syllabus once again, you want to understand, that is something like up and down, no. It's not easy to do that story, but this is the way that we are doing, right? But even today's revision also, right? Anyone at any level, if you miss the previous theory point, if you forgot the previous theory point, today I think I tried my maximum to make everything understandable. I hope everyone understood these ideas. Today we covered, even though we start the class at 7:30, normally we are starting at 7 o'clock hereafter, daily 7 morning. Then what we have done is, no, because parallel you want to do the remaining lessons also properly, no. Today we covered unit 4. This month parallelly I am doing unit 4 heat and unit 6 electric field revision. Both units we are going parallelly, and also if I have enough time I will do some mechanics sections. Also I will do mechanics some sections revision also from this April month. But the most important thing is this paper class is very important, past paper class very important. From that past paper class you can get a good exposure, right? Then special full paper class, right? No, for somehow we have 4 months, somehow I will do with my best, okay? With my best I will do everything for you, get the maximum benefit. Get the maximum benefit, right? That's the way. Now these 4 months, unconditionally you want to work. I don't want to tell you that how the way that you want to work for these 4 months. You guys know that if you don't work for these 4 months, what will happen to you guys can imagine. No? People who are already doing second shy, third shy, they know the situation. If it is the first time that you are doing the exam, sometimes still you are not very aware about the real condition that you are facing right now. But very soon you will realize the story. Okay, then we'll meet today. Okay, I think just give a small feedback about the session with the, is it okay, this revision is fine? No, because this is the best way that I can deliver entire content syllabus within this 3.5 months. This is the best way that I can do. And also the practical story, calmly, slowly I'm doing, don't worry. Then put a small feedback also. Put a small WhatsApp message if you have enough time. Put a WhatsApp message whether how was the revision day today. Put a small reply. And tunes and all you will get maximum within 1 week, 1 week. Sometimes it might change here and there, but anyhow for this April month you'll get tunes for sure. That is sure, no doubt. Right, then put a small reply also. Then we can stop the class for today. Study well unconditionally. That's what I can tell. Then have fun. We'll meet today 6 p.m.